Hello, fellow sapiens, and welcome to Sleepless Homo. Whether you're preparing to sleep, winding down after a long day, or simply relaxing while cooking, showering, or working with headphones, this channel is here to calm your mind with science told softly. If you appreciate this kind of thoughtful, long-form content, please consider liking and subscribing. It helps more people discover educational stories that bring comfort and knowledge instead of noise. And if you drift off mid-chapter, no problem. I've left timestamps in the description so you can find your way back the next day because each chapter builds the full story. Remember, this is not about wild speculation but humble science, carefully told. We don't always have all the answers, but we'll follow the evidence wherever it leads. And as always, stay curious, stay calm. Tonight's story: the Younger Dryas Impact Hypothesis. Did a comet end the Ice Age, or just our mammoths? Imagine the scene. Glaciers that had been retreating for millennia, rivers of meltwater coursing across continents, valleys opening to tundra and grasslands where herds of animals moved in seasonal cycles. Humanity, scattered in small bands across Europe, Asia, and the Americas, was beginning to feel a rare reprieve. For several thousand years after the peak of the last glacial maximum, the climate had been slowly shifting into something more livable. And then, just as the planet appeared to be climbing into stability, temperatures plunged. Why? The period we call the Younger Dryas began roughly 12,900 years before the present, and it lasted until around 11,700 years before the present. It is a peculiar event in Earth's history, and it stands out because of its abruptness. The cooling began in a geological instant. Within just a few decades, perhaps even within a single human lifetime, the northern hemisphere grew colder by as much as 6 degrees Celsius. For people living through it, this would not have been an abstract curve on a graph. It meant ice advancing back into valleys they thought were free. It meant shorter summers, harsher winters, and ecological zones shifting hundreds of kilometers almost overnight. To appreciate the shock of this reversal, we need to place it against the backdrop of the last glacial maximum. About 20,000 years ago, massive ice sheets had reached their greatest extent across North America and Eurasia. They locked up so much water that global sea levels dropped by over 100 meters, exposing continental shelves and altering coastlines. By about 14,700 years ago, these ice sheets began to collapse, and the planet warmed in fits and starts. This warming is known as the Bulling-Allerud interstadial, a brief interglacial pulse that lasted for around 2,000 years. Forests expanded northward, herds followed them, and humans took advantage of the opening landscapes. It seemed like the glacial world was retreating for good. Then, with little warning, the warmth ended. Greenland ice cores show this vividly. When scientists drilled through 2 kilometers of frozen record, they uncovered clear signals of climate change preserved in the layers of snow and ice. These layers tell us that the Younger Dryas was not just a slight chill, it was a plunge back into near-glacial conditions. The isotopic ratios of oxygen in the ice shift suddenly, a proxy for temperature that allows us to reconstruct how cold it became. This is the kind of data that humbles us. The planet can flip in less than a human generation, overturning ecosystems and forcing every species to scramble. But the Younger Dryas was not evenly felt everywhere. The northern Atlantic region bore the brunt of it. Europe grew colder and drier, with glaciers re-advancing into high valleys. Britain, already chilly, became almost uninhabitable in parts. Yet the southern hemisphere experienced something different. In places like Australia, there is little evidence of such a cooling. Some regions may have even grown wetter. Antarctica's records tell a more complicated story, with minor shifts, but nothing as dramatic as in the north. This asymmetry hints that the cause was not a global dimming of the sun or some planetary-scale volcanic blackout, but something more local to the northern hemisphere's climate system. For those living through it, the suddenness must have been disorienting. We can imagine hunter-gatherer communities in Europe already adapting to forests where reindeer had retreated north, now watching as tundra returned almost overnight. In North America, ecosystems that had been expanding after the ice's retreat suddenly froze again, reshaping the ranges of animals and plants. Rivers swollen with glacial meltwater shifted course, new lakes appeared, and dry winds scoured landscapes once green. The Younger Dryas is sometimes described as a cold snap, but that phrase hardly conveys what a plunge of several degrees meant in real life. It was a shift so strong it delayed the end of the Ice Age by more than a millennium. When we ask what made this happen, we find ourselves at a frontier of paleoclimate science. The story is still unfinished. What we know with some certainty is that the abruptness points to a tipping point in Earth's systems, rather than a slow orbital drift. The cycles of Earth's tilt and orbit, known as Milankovitch cycles, do explain long swings between glacial and interglacial periods. But the Younger Dryas does not fit neatly into that rhythm. Instead, it looks like the planet stumbled over a threshold. Something in the North Atlantic system broke or jammed, halting the flow of warmth northward. Ice core records show not only temperature changes, but also chemical fingerprints that help us understand the atmosphere of the time. Alongside the drop in oxygen isotope values, there are spikes in dust and in certain chemical species that suggest increased winds and aridity. In lakes across Europe, sediment layers shift abruptly from warm-loving plant pollen to cold-resistant species. In marine cores from the Atlantic, the tiny shells of Foraminifera, microscopic organisms that build calcium carbonate tests, show temperature swings that match the ice record. Taken together, these proxies leave little doubt. The Younger Dryas was real, global in extent and abrupt in onset. The name Younger Dryas itself comes from a small alpine flower, Dryas octopetala. Its pollen is abundant in the layers dated to this time in Europe, showing how tundra species reclaimed ground from temperate forests. There is also an older Dryas, and even an oldest Dryas, shorter cold phases during the deglaciation. But the Younger Dryas was the last and most dramatic of them, a final gasp of glacial climate before the Holocene, the warm epoch in which we still live, took hold. What makes this event so fascinating is that it came at the hinge of human prehistory. Around this time, people in the Levant had begun experimenting with wild cereals, laying the foundations of agriculture. In Europe, small communities were dispersing north as forests spread. In North America, human groups were establishing themselves in landscapes still dominated by megafauna. The Younger Dryas interrupted all of this, reshuffling the ecological and cultural board. It was a cold intermission just before humanity's great shift to farming and permanent settlements. The suddenness of the onset remains one of the puzzles. Was it a matter of a few decades? Ice core data suggests so. That means children could have grown up in one climate and found their adulthood framed by another. It is hard not to wonder what oral traditions, if any, might have carried faint echoes of this experience, memories of winters deepening and summers failing. The archaeological record cannot give us those stories, but the climate data hints at them. As scientists, we must remain humble here. We can say with confidence that the Younger Dryas happened, that it was abrupt, and that it reshaped both natural and human histories. But why it began so suddenly remains open to debate. Later in this journey, we will examine the proposed causes, from freshwater floods disrupting ocean currents, to volcanic clusters, to more exotic explanations. For now, it is enough to recognise the strangeness of the event itself. The world was warming, ice sheets were in retreat, and then, as if tripped by some unseen lever, the planet tumbled back into 1,000 years of cold. And so we end this part of the story with a question that still lingers in the minds of scientists. What hidden switch in Earth's climate system was flipped 12,900 years ago, plunging the northern hemisphere back into glacial chill, just as it seemed the Ice Age was over? How do we know the Younger Dryas even happened? It is easy to talk about sudden chills and ancient winters, but without some reliable record, all of this would remain only speculation. The key to our understanding lies in ice. In Greenland, thousands of meters of compacted snowfall have built a natural archive of the planet's climate. Each year's snow carries the chemical imprint of the atmosphere, the dust and salts carried by winds, and the isotopes of water vapour that reveal the temperatures from which the snow fell. These layers stack up like the pages of an enormous book, buried deep under the weight of later snow. To read it, scientists have drilled through 2 kilometres of solid ice, extracting cores that span more than 100,000 years of Earth's climate history. When these ice cores were first analysed in the late 20th century, what emerged was startling. Instead of a smooth, gradual curve of climate change, the oxygen isotopes told a story of sharp jumps and falls. The isotope most used, oxygen-18, is slightly heavier than oxygen-16, and the ratio between them varies depending on temperature. When water evaporates from the oceans and falls as snow at high latitudes, colder conditions favour lighter isotopes, leaving a signal in the snow that can be measured thousands of years later. By slicing through the layers of the ice cores and measuring the ratios, scientists could reconstruct temperature changes with astonishing precision. It was in these records that the Younger Dryas revealed itself as a sudden plunge. The isotope curves drop almost vertically at around 12,900 years before the present. Within perhaps as little as a single human generation, Greenland grew several degrees colder. Then, about 11,700 years ago, the line shoots upward again, marking the end of the event and the beginning of the Holocene epoch. There is no mistaking these shifts. They are as clear as a heartbeat on a medical monitor, only stretched across millennia. The precision of the dating is worth dwelling on. Layers in the ice cores can be counted like tree rings, especially in the more recent sections where annual layers are distinct. In some intervals, volcanic eruptions leave sulfate spikes that act like timestamps, cross-checked against other records. By combining layer counting with radiometric methods and comparisons to known volcanic events, researchers can align the Younger Dryas within a narrow window. The beginning is placed around 12,900 years ago, and the end around 11,700 years ago, making its duration roughly 12 centuries. This is a remarkable level of resolution for an event that happened so far in the past. What struck the scientific community most when these records first came to light was the abruptness. For much of the 20th century, climate was often thought of as sluggish, responding slowly to orbital changes or tectonic shifts. The Greenland cores showed otherwise. Climate could jump, it could pivot within decades, possibly within years. That discovery altered the way we think not just about the past, but also about the stability of our own present. If such dramatic shifts could happen in prehistory, the possibility of a rapid change today cannot be ignored. As the cores were studied in greater detail, patterns emerged. The Younger Dryas was not alone. Scattered throughout the last glacial cycle are a series of abrupt warming and cooling swings now known as Dansgaard-Oeschger events, after the scientists who first identified them. These are repeated patterns in the ice record, a rapid warming over a few decades, followed by centuries of gradual cooling, and often capped by a sudden plunge. They appear about 25 times in the Greenland record over the last 100,000 years. The Younger Dryas is the final and most famous of them, because it occurred just as the planet was transitioning out of the Ice Age. But it is important to note that the cores also reveal regional contrasts. The isotope story from Greenland is dramatic, but records from Antarctica show nearly the opposite. When Greenland cools, Antarctica often warms, and when Greenland warms, Antarctica cools. This bipolar seesaw is thought to reflect changes in ocean circulation, with heat being stored in one hemisphere while the other grows cold. The Younger Dryas fits neatly into this larger rhythm, reinforcing the idea that the event was not a quirk of Greenland alone, but part of a global system of climate shifts. Other proxies strengthen the case. In European lake sediments, pollen grains show forest retreating, and tundra plants returning at the onset of the Younger Dryas. In marine cores from the North Atlantic, the shells of tiny plankton record cooling surface waters. Even speleothems in caves, stalagmites and stalactites, preserve chemical signals of the changing climate, with growth slowing during the cold centuries. These multiple lines of evidence align with the ice cores, creating a robust picture. The Younger Dryas was real, it was abrupt, and it reshaped environments across the Northern Hemisphere. Of course, knowing that it happened is not the same as knowing why. That question remains unsettled, and we will explore the competing explanations later. For now, what matters is the clarity with which the ice cores capture the event. They are time machines in the truest sense, giving us access to winters and summers that fell long before written history. They show us that climate is not a smooth slope, but a staircase, with sudden drops and unexpected landings. When researchers first presented these findings, they met with skepticism. The idea that climate could change so abruptly seemed implausible, but as more cores were drilled, and as different laboratories confirmed the isotope signals, the reality of the Younger Dryas became undeniable. It is now one of the best documented events in quaternary science, serving as a case study in how sensitive the Earth system can be. And yet, despite the clarity of the graphs, a question lingers. If climate can lurch so suddenly, what was the trigger? Was it a collapse of ocean currents, a pulse of fresh water, a chain of volcanic eruptions, or something more unusual? The ice cores tell us the timing and the magnitude, but they do not tell us the cause. For that, we must turn to other lines of evidence, and that search has fueled decades of debate. As we stand with these ice cores, looking back 12,900 years, we cannot help but wonder, if you were alive then, would you have noticed the change in your own lifetime? Would you have felt the winters deepen and the summers shorten, or would it have crept in so subtly that only your grandchildren realised the world had shifted? The cores suggest it was fast, but lived experience is another matter. Perhaps somewhere, someone remarked that the rivers froze longer than before, that the trees bore fewer leaves, that the herds moved differently. Those voices are lost to us, but the ice has preserved their silence in isotopic codes. The Younger Dryas is written into the frozen pages of Greenland, a reminder that the climate system is full of surprises. We read it now with the tools of science, but it is still, at its heart, a mystery story. We know when it began and when it ended. We know how cold it grew, but the deeper why remains unsettled. That uncertainty is not a flaw in the record. It is the honest edge of knowledge, where questions point the way forward. The story of the ice cores is not only about their chemical messages, but also about the sheer challenge of retrieving them. Drilling into the Greenland ice sheet is like trying to open a vault of time. Teams of researchers work in freezing conditions, far from any settlement, guiding hollow drills slowly downward. Each section of ice brought to the surface is carefully logged, wrapped and stored. The clear cylinders often look like nothing more than frozen glass, yet inside them are trapped tiny bubbles of ancient air. These bubbles are the only direct samples of Earth's past atmosphere that we possess. They carry the concentrations of carbon dioxide, methane and other gases as they were tens of thousands of years ago. When the Younger Dryas interval is reached in the cores, these air bubbles tell their own story. Methane levels drop abruptly, reflecting the collapse of wetlands in the cooling north. Dust levels rise, showing that winds became stronger and landscapes drier. These shifts add texture to the temperature record, confirming that what the isotopes suggest was mirrored in the wider environment. The value of this is that it rules out the possibility that the Younger Dryas was some artifact of measurement. The signal is too consistent across gases, dust and isotopes to be a laboratory illusion. The ice also provides annual resolution in some sections, thin bands that can be counted one by one under a microscope. This fine detail reveals that the transitions into and out of the Younger Dryas were not slow fades. The onset seems compressed into just a handful of layers. The exit into the Holocene is even sharper, an almost vertical rise in isotope values that speaks of a world warming in the blink of a geological eye. Such evidence has pushed scientists to rethink what abrupt really means in climate science. It is not centuries, but perhaps mere years that separate one state from another. Another layer of intrigue comes from how the cores synchronize with other records. In Japanese lake sediments, in North Atlantic marine cores, in stalagmites from China and Oman, signals line up with the same timing as the Greenland plunge. These cross-checks mean the Younger Dryas is not an isolated Greenland phenomenon, but a hemisphere-wide event. The cores thus act as a central spine to which other paleoclimate records can be pinned, creating a coherent timeline that spans continents. What humbles many researchers is how these records make us rethink scale. From the human point of view, a millennium is unimaginably long. From the planet's perspective, it is the flick of a switch. The ice reminds us that climate systems have thresholds, points at which they reorganize with startling speed. And so, we return to the haunting question. If such a shift could erupt from Earth's own rhythms 12,900 years ago, how stable is the warmth that cradles us now? What did the Younger Dryas actually feel like on the ground for those who lived through it? Numbers and graphs pulled from the ice cores can show dramatic plunges and abrupt spikes, but for the hunter walking across the tundra or the family huddling in a rock shelter, climate was not an isotope. It was wind against skin, ice returning to valleys, forests thinning to scrub. around 12,900 years ago, as the planet's northern latitudes should have been easing into gentler conditions, the sudden reversal sent Europe and much of the North Atlantic world back into a hard freeze. Glaciers that had been shrinking turned around and began to creep forward again. Alpine valleys in Switzerland that had been greening during the Allerud interstadial were once more filled with advancing ice tongues. In Britain, cold-tolerant plants that had retreated south suddenly returned, and pollen trapped in ancient lake beds tells us that birch and juniper again became dominant as oaks and hazel failed to thrive. The chill was not only cold but also dry. The Younger Dryas brought with it sharp reductions in rainfall across much of northern Europe and the eastern side of North America. Lakes shrank, rivers became sluggish, and the landscapes grew dusty. From the perspective of a reindeer herd, this meant pastures changed abruptly. Moss and lichen, once made available by warmer winters, were now locked under snow and ice. Hunters following those herds would have found migration routes altered or broken entirely. In some areas, the abundance of certain animals may even have increased at first, as cold ecosystems stabilized briefly. But the unpredictability of the seasons made human planning far more difficult. Yet the changes were not uniform across the globe, and this asymmetry is part of what makes the Younger Dryas so fascinating. In the southern hemisphere, the story diverges. In parts of South America, such as Venezuela, lake sediments show cooler conditions, but across large stretches of the continent and in southern Africa, evidence points to relative stability, or even mild warming. Antarctica tells an even stranger tale. The ice cores there show a pattern almost the reverse of Greenland's, with warming aligning with northern cooling. In New Zealand and southeastern Australia, some records suggest that rainfall may actually have increased during this same interval. What this means is that the Younger Dryas was not a single global freeze but a seesaw, with one hemisphere plunging back toward glacial conditions, while the other experienced something quite different. This contrast shows up clearly in the pollen records from Europe compared to those from Africa or South America, and it also appears in the chemical markers trapped in stalagmites from far-flung caves. One half of the planet was lurching into harsh winters, while the other seemed relatively spared. To people living in northern latitudes, it would have been felt as a betrayal of the warming trend that seemed to promise a gentler world. To those in the southern hemisphere, the event might not have registered at all as anything extraordinary. And to us today, the haunting question remains: what kind of planetary system allows one hemisphere to stumble backward into ice, while the other stands in place, or even warms? It suggests a climate engine capable of shifting gears differently north and south, with consequences that were and still are unevenly distributed. The unevenness of the Younger Dryas becomes even clearer when we look not only at temperatures but at ecosystems. In Central Europe, less deposits, the windblown silts that cover wide tracts of land, accumulated more rapidly, meaning dust storms scoured the surface as vegetation failed to anchor soils. In the American Midwest, ancient lake basins show fluctuating water levels that signal harsher drought cycles than had been seen for thousands of years. To live in these landscapes meant not only enduring colder winters, but facing unpredictable rainfall, failing crops of wild grains, and the need to move constantly in search of sustenance. This was not a return to the steady cold of the last glacial maximum. It was a jittery, unstable world in which one year might bring brutal storms and the next parched ground. Meanwhile, in places far removed from the ice sheets, life went on with far less drama. In tropical Africa, sediment cores from Lake Victoria and Lake Tanganyika show evidence of modest shifts, but the broad outlines of climate remained steady. Plants continued to grow in abundance, animal populations stayed relatively stable, and human groups there probably carried on with minimal disruption. For them, the Younger Dryas was perhaps no more than another turn in a long sequence of seasonal challenges. What is striking is that even within a single continent, the impact varied sharply. In South America, the high Andes cooled noticeably, forcing alpine plants and animals to descend to lower altitudes. But in the Amazon basin, wetter conditions may have supported flourishing forests. This patchwork of responses is a reminder that global climate events are never experienced evenly. Local geography, altitude, and prevailing winds determine whether an area suffers or survives. Archaeological traces give us small but telling glimpses of how people adapted to these microclimates. In northern Spain and southern France, where cave sites preserve layers of human occupation, The Younger Dryas appears as a time of shifting toolkits and food sources. Hunters relied more on cold hardy species such as reindeer, and less on red deer or boar, which retreated with the forests. In contrast, communities in the Levant were already experimenting with harvesting wild cereals, and pollen records suggest they had to cope with drying conditions by moving seasonally to follow remaining patches of fertile land. Even marine environments tell a story. Shell middens along the coastlines of Japan and Korea record changes in which mollusk species dominated. Some warm water species declined, replaced by those adapted to colder seas. For coastal people depending on shellfish, these subtle changes altered not just diet but the rhythm of daily foraging. Such evidence reminds us that the Younger Dryas was felt in oceans as well as on land, in fisheries as much as in forests. Taken together, these clues paint a portrait of a world divided. The northern hemisphere shivered, glaciers crept forward, winds scoured plains, and hunters faced landscapes that betrayed their expectations. South of the equator, many communities experienced less disruption, and in some cases, climates may even have become more favourable for growth. The asymmetry is not only scientifically intriguing, it also forces us to think about the unevenness of human history. Survival and adaptation are never global in the same way. Where one group is pressed to the brink, another continues almost unchanged. The haunting thought is this. If you had been born 12,800 years ago, the story of the Younger Dryas would have depended entirely on where you were standing. In Britain or Scandinavia, you would have watched forests vanish and ice return. In Kenya or Peru, you might have carried on, barely aware of the upheaval half a planet away. That dissonance is a reminder that climate is not a single story, but many overlapping ones, bound together by a complex Earth system. And we are still unravelling how those stories interacted. Did the southern stability soften the blow of northern chaos by serving as a reservoir of biodiversity? Or did it simply mean that history forked, with one half of the human world thrown into turmoil while the other continued undisturbed? We cannot yet say with certainty. But the evidence we do have shows that the Younger Dryas was not a single blanket of cold draped over the Earth. It was a quilt of extremes, stitched together by forces we are only beginning to understand. Imagine standing on a plain in North America 13,000 years ago. The cold of the Younger Dryas has just begun to creep back, but the land is still populated by giants. Herds of woolly mammoths graze on coarse grasses, their tusks curving in sweeping arcs. Mastodons, stockier and adapted to browsing on shrubs, move through patches of woodland. Saber-toothed cats with their improbable fangs watch from the shadows, while enormous short-faced bears, heavier than any living grizzly, patrol river valleys. Horses, camels, and ground sloths, some of them the size of small elephants, are all part of this crowded stage. To us, this world sounds fantastical, as though lifted from myth, but it was real, and it was within the last heartbeat of geological time. By 13,000 years ago, such megafauna still existed on nearly every continent. In Europe, woolly rhinoceroses persisted alongside mammoths, though in declining numbers. In South America, giant ground sloths like Megatherium still lumbered across grasslands, accompanied by armoured glyptodonts with shells as heavy as a small car. In Australia, the last populations of giant kangaroos and the formidable marsupial lion had already vanished thousands of years earlier, leaving that continent's landscapes quieter. Yet the Americas, Eurasia, and scattered islands still carried the legacy of the Ice Age giants. The timing of their disappearances is one of the great puzzles of prehistory. Radiocarbon dating of bones, tusks, and dung deposits shows a pattern that is not uniform but staggered. In North America, mammoths seem to have dwindled rapidly around the window of the Younger Dryas, while horses and camels vanished completely from the continent. Mastodons disappeared somewhat earlier in certain regions, but survived in others until roughly the same period. In Eurasia, mammoths held on in isolated pockets long after the cooling began, with tiny populations persisting on Wrangel Island in Siberia until just 4,000 years ago, long after the pyramids of Egypt had been built. What this reveals is that extinction was not a single synchronized event. Some species declined before the Younger Dryas, others during it, and a few clung to existence long after. Yet when we view the broad picture, Many of the most iconic megafauna vanish from the fossil record between about 13,000 and 11,000 years ago, placing their final struggles in the same time frame as the sudden climatic reversal. That overlap has invited speculation for more than a century. Did the shock of returning cold tip already fragile species into collapse? The environmental evidence gives us clues. The onset of the Younger Dryas brought drier, colder conditions to much of the north. For grazers like mammoths, already pressed by shrinking grasslands as forests encroached during earlier warming, the sudden freeze may have reduced available food even further. For giant sloths in the Americas, the shift likely altered the composition of plants they relied on. Predator species, dependent on stable herds of a large prey, would have felt the knock-on effects of dwindling numbers. The entire fabric of ecosystems, already stretched thin by millennia of fluctuating climate, may have been torn by one last jolt. Still, it would be misleading to imagine all extinctions as simultaneous or caused by one simple trigger. In South America, some megafauna disappear slightly later than in North America, suggesting regional dynamics. In parts of Eurasia, mammoths and woolly rhinoceroses were clearly declining before the Younger Dryas even began. The pattern is messy, with local habitats and ecological niches playing decisive roles. This complexity leaves us humbled. It is tempting to tell a single sweeping story of sudden death, but the evidence insists on a mosaic of fates. What is undeniable is that by the close of the Younger Dryas, the stage of the world was dramatically emptier. The great animals that had dominated the Pleistocene for hundreds of thousands of years were gone or reduced to remnants. Landscapes that once echoed with the footfalls of giants became quieter, and ecosystems rebalanced towards smaller, more adaptable species. The loss reshaped not only the natural world, but also the lives of humans who had shared their territories with these animals. For them, the disappearance of megafauna meant the loss of both threat and resource. The haunting question lingers: were these creatures already doomed by long-term climate instability, with the Younger Dryas only accelerating their fall? Or was this sudden cold snap the decisive blow that ended the reign of the giants? We cannot answer with certainty, but the overlap in timing ensures that the Younger Dryas remains forever linked with the last chapter of the mammoths, the saber-toothed cats, and the towering sloths. What makes the story even more compelling is how traces of these vanished animals still surface in the most unexpected ways. Caves in the American West preserve layers of dung from ground sloths, stacked year after year until their sudden absence marks the end of the species. Frozen steppe soils in Siberia hold entire mammoth carcasses, their stomachs filled with the grasses they ate in their last days, frozen so quickly that even their hair and soft tissue remain. Peat bogs in northern Europe yield the antlers of giant deer, also known as the Irish elk, animals whose racks stretched wider than the span of a human arm outstretched twice. Each of these finds is a snapshot, a reminder that the Ice Age giants were not distant myths but flesh and blood creatures sharing the same landscapes as our ancestors. The timing of these disappearances also intersects with broader ecological transformations. When mammoths vanished from the steppe tundra, the landscapes they once kept open by trampling and grazing began to change. Birch and willow colonized the ground more freely, reshaping the ecosystems that followed. Without the armored glyptodonts in South America, grazing pressures on grasslands shifted, opening opportunities for smaller herbivores. Extinction was not simply subtraction. It was a restructuring of environments that rippled forward into the Holocene. Another clue to the uneven tempo of extinction comes from islands. Isolated from mainland pressures, populations sometimes lingered far beyond their continental cousins. The tiny mammoths of Wrangel Island are the best known, but similar patterns appear elsewhere. In the Channel Islands off California, pygmy mammoths survived until roughly the same period as Wrangel's herds. On Caribbean islands, giant ground sloths endured until nearly 5,000 years ago. These survivors reveal that extinction was not inevitable at a global scale all at once. Context and geography mattered profoundly. The story of the megafauna at the onset of the Younger Dryas is thus not a single obituary but a patchwork of final acts. Some animals were in decline long before the cooling began, some collapsed within its grip, and others persisted long after. To us, looking back through the narrowing keyhole of the fossil record, it is tempting to blur these stories together into one catastrophic ending. but the truth appears subtler, a cascade of endings spread across centuries and continents, bound together by the shared fate of giants in a world that no longer had room for them. And so we are left with a poignant vision, a world half in winter, half in spring, where mammoths still roamed in one valley even as they disappeared forever in another. To the humans who witnessed them, these creatures must have seemed eternal and their absence unimaginable. Yet within a few short centuries, the world's great stage was emptied of its largest actors, and the curtain fell on an age of giants. If the cold winds of the Younger Dryas pressed hard on mammoths and ground sloths, they pressed just as firmly on the scattered bands of humans trying to make their lives in landscapes that shifted beneath their feet. Around 12,900 years ago, groups across the northern hemisphere had only just begun to enjoy a respite from the long chill of the last glacial maximum. In the Americas, toolmakers known to us through the fluted spearheads of the Clovis culture hunted game in vast plains that had recently thawed and sprouted with grasses. In the Levant, villages of the Natufians experimented with a kind of sedentism, harvesting wild cereals and building stone houses that suggested life might at last become more predictable. In Europe, hunters had moved into valleys abandoned by ice, and in Britain, burials mark a people living close to rivers and caves. The sudden reversion to glacial conditions must have felt like a betrayal of hope. The question is, how did they react? The Clovis culture has become a touchstone in this story because of its distinctive tools, long fluted spear points, shaped with a skill that allowed hunters to thrust or throw them into the hides of the large animals. For a time, these tools appear across much of North America, a sign of shared ideas or widespread mobility. Yet by the opening centuries of the Younger Dryas, the archaeological record shows Clovis fading, replaced not by empty landscapes but by a patchwork of newer traditions. Folsom points, smaller and more refined, appear in the Great Plains, tailored for bison rather than mammoth. In the American Southeast, other styles emerge. The transition does not look like sudden disappearance, but rather adaptation, as communities shifted prey, refined technology, and adjusted to shorter growing seasons and harsher winters. The landscapes were still inhabited, but the Clovis name no longer defined them. In the Levant, the Natufians were among the first humans to build stone houses and invest in permanent villages. Before the cold struck, they harvested stands of wild wheat and barley, collecting seeds with flint sickles and storing them in pits. Their settlements grew larger, and some archaeologists argue that these communities were already experimenting with the first steps toward agriculture. Then the Younger Dryas altered the equation. Drought replaced relative abundance, woodlands shrank, and game shifted ranges. Some Natufian sites appear to contract or be abandoned. Others suggest a return to mobility, with groups leaving behind heavy stone houses in favour of lighter shelters that could be moved seasonally. Yet the foundation remained. They continued to harvest cereals, they continued to gather nuts, and when conditions warmed again, their descendants were poised to take the leap into full cultivation. In this way, the cold snap may not have ended their trajectory, but rather forced a pause that sharpened resilience. Britain presents a mystery of a different sort. Before the Younger Dryas, burials are found with relative frequency. Graves in caves, sometimes accompanied by tools or ornaments. After the cold took hold, the record falls silent. For centuries no burials are known. And yet the land was not empty. Tools, butchered animal bones, and worked flint tell us people remained. Explanations vary. Perhaps groups moved to the coasts where rising seas have since swallowed their cemeteries. Perhaps burial practices changed, shifting to methods that leave little trace, such as exposure of bodies on the surface rather than inhumation. Perhaps the population dwindled so dramatically that few bodies were left to be found. Each possibility leaves us with an unsettling gap, a reminder that climate disruption can erase not only communities, but even the traces they leave behind. Elsewhere, the impact of the sudden cold is visible in subtler ways. In East Asia, populations may have shifted southward, adjusting to colder, drier conditions. In South America, early sites show continuity, but with signs of stress as large animals became scarcer. These stories suggest a pattern. The Younger Dryas did not erase humanity, but it did demand rapid flexibility. Communities that could pivot, altering prey, experimenting with new tools, or even uprooting themselves entirely, were the ones that endured. The larger picture is one of human tenacity. We are, after all, the species that endured ice sheets, deserts, droughts, and floods, long before written history began. The Younger Dryas was one more trial in a long sequence, but the timing matters because these were not just foragers clinging to survival. In multiple regions, they were beginning to reshape their relationship to land, food, and each other. A colder, drier millennium interrupted that process, delaying some trajectories while accelerating others. When the warmth returned, the seeds, sometimes literal ones, were ready to sprout into new forms of society. It is humbling to imagine what this must have felt like on the ground, to live in a stone house for the first time, only to abandon it again when crops failed, to bury your dead in one generation and then stop, leaving no trace for archaeologists to find, to hunt mammoths with weapons perfected over centuries, only to discover they had vanished from your valley. The Younger Dryas reminds us that cultural progress is never linear. Climate can pull the rug from beneath even the most promising experiments, forcing resets, migrations, and improvisations. The haunting question remains: how many paths of human possibility were extinguished in that 1,000-year chill, and how many were forged precisely because of it? If we look beyond the better-known centres of archaeology, the Younger Dryas also left quieter imprints that help us sense the breadth of its disruption. In the highlands of Anatolia, cave deposits suggest fluctuating use during this period, with occupations appearing sporadically and then vanishing for centuries. These gaps may hint at groups oscillating between upland and lowland zones, as winters lengthened and food webs contracted. In the Caucasus, obsidian tool scatters suggest that mobility increased, perhaps reflecting a return to smaller, more flexible hunting parties, rather than the larger groups that had clustered during the milder centuries before. These shifts show that resilience was not uniform. Different regions generated their own survival strategies, each shaped by microclimates and available resources. Across northern Europe, pollen records reveal dramatic contractions of forests. Where birch and pine had begun to reclaim open ground, tundra species suddenly resurged, rolling back the green frontier. For humans, this meant that familiar landscapes altered within a few generations. Game animals retreated or grew scarce, and new hunting grounds had to be discovered. The archaeological record registers this not in sudden collapse, but in the scattering of sites, as if families pulled back into smaller ranges, eking out a living at the edges of habitable zones. Such retreats may also explain why the number of preserved artifacts appears to drop. Fewer people left fewer traces, or they moved so often that their campsites were ephemeral. The picture in North Africa is less clear but equally intriguing. Lake cores in the Sahara indicate that arid conditions intensified, shrinking the oases that had served as lifelines for scattered foragers. At the same time, evidence from the Nile Valley shows continued human presence, with grinding stones and hearths suggesting persistent adaptation to fluctuating water levels. Here, the Younger Dryas did not bring glaciation but instability. Sometimes too much water, sometimes too little, forcing people into a constant balancing act. In this sense, the period was not a single story of cold, but a global patchwork of disruptions, each demanding different human responses, even in areas buffered from the worst of the cold, such as parts of East Africa or South Asia. The ripple effects mattered. Shifts in rainfall patterns altered plant communities, making some areas more attractive and others less. Hunter-gatherers had to track these changes closely, moving season by season to ensure continuity. It is likely that oral traditions, honed over generations, carried memories of where to find resources when conditions worsened. In this way, knowledge itself became a survival tool, passed between elders and the young as carefully as a stone blade. Taken together, these glimpses remind us that the Younger Dryas was not just a matter of ice and graphs in Greenland. It was a lived reality that fractured into countless local stories. Families abandoning stone houses, children growing up in harsher winters, elders recalibrating knowledge of where to hunt or gather. Some stories we can trace in stone tools or pollen grains. Most are lost, and yet the survival of our species through this 1,000-year detour tells us they found ways forward, even when the climate itself seemed intent on erasing the ground beneath their feet. When scientists first tried to explain the abrupt cooling of the Younger Dryas, they did not look to the sky but to the oceans. The Earth's climate system is not only about sunlight and atmosphere, but also about water constantly moving across the globe. Heat is carried not only by winds but by deep currents, and in the North Atlantic this process is particularly powerful. Warm surface water flows north from the tropics, releases its heat to the air, and then sinks as it cools and mixes with saltier water. This sinking drives a global conveyor belt, the Atlantic Meridional Overturning Circulation, or AMOC. It is not just a current, but the backbone of heat distribution across hemispheres. Without it, winters in Europe would be far harsher, monsoon systems would shift, and the tropics themselves would change. In short, the conveyor is one of the quiet but essential gears of the climate machine. Around 12,900 years ago, something appears to have interrupted that gear. The leading suspect is not mysterious at all: meltwater. At the close of the last glacial maximum, as ice sheets retreated across North America, they did not simply melt in place. They released torrents of water that pooled into vast proglacial lakes. Among them was Lake Agassiz, a body of water so large it dwarfed modern Great Lakes combined. As long as the ice sheets dammed it, Agassiz was contained. But ice dams are fragile. When they break, they release floods that can transform entire continents in weeks. Geologists studying old shorelines and sediment fans have long debated whether, at the onset of the Younger Dryas, Lake Agassiz spilled catastrophically into the North Atlantic. Two possible escape routes have been proposed. One leads through the Mackenzie River Valley, northward into the Arctic Ocean. If water surged this way, it would have poured across a landscape that today lies in Canada's Northwest Territories, racing through tundra channels into the Arctic seas. Another path lies eastward, through the St. Lawrence River and directly into the North Atlantic. Either way, the result would have been the same: an enormous pulse of fresh water entering saltwater circulation. Fresh water is less dense than salty water, and if too much floods into the system at once, it prevents surface waters from sinking. That is the key to the conveyor belt. No sinking, no pull, no circulation. The ocean's great pump grinds to a halt. Sediment cores from the North Atlantic provide some backing for this theory. Layers dating to the Younger Dryas show shifts in the tiny shells of foraminifera, microfossils whose chemical makeup reflects ocean temperatures and salinity. Some layers suggest surface waters freshened abruptly. Pollen records on land match this with sudden cooling in Europe. Together, these hints make a compelling case. The conveyor belt stopped, and the North Atlantic descended into a millennium of cold. Yet even here, as in so much of climate history, the details are not straightforward. If the water went north through the Mackenzie route, its effects would have been strongest in the Arctic Ocean. Models show that this could still disturb circulation, but the signal would be indirect. If instead the St. Lawrence route carried the flood, the interruption would have struck the North Atlantic directly. Both scenarios could explain cooling, but both require enormous volumes of water at just the right moment. Geologists argue over dates. Did Agassiz drain precisely at 12,900 years ago, or earlier, or in multiple pulses spread over centuries? Some lake shorelines suggest gradual releases rather than single catastrophic floods. Others hint at sudden drainage events. Without a precise calendar, the connection between these floods and the Younger Dryas cooling remains a hypothesis. Another complication comes from the southern hemisphere. Ice cores from Antarctica show that when the north cooled, the south warmed. This seesaw pattern, known as the bipolar seesaw, makes sense if the conveyor shut down. Heat that would normally travel north remained in the southern oceans instead. But here again, the signal is not perfectly aligned. Some Antarctic records suggest warming began before the Younger Dryas, as if the climate machine was already shifting. This has led some researchers to ask whether the conveyor slowdown was cause or consequence. Did freshwater shut it down, or was it already unstable, with meltwater only nudging it over the edge? The freshwater hypothesis remains one of the most studied explanations because it ties together ocean physics, glacial melt, and observed climate records. It is simple, in principle. Too much fresh water and the pump stops. Yet simplicity can be deceptive. The volumes required are staggering, and the precision of timing matters. If even a few centuries separate the flood from the cooling, the neat cause and effect picture phrase. So we are left with a plausible culprit, but not a fully proven one. The conveyor belt theory explains much, but not everything. And so the haunting question lingers. Did the oceans themselves, overwhelmed by the melting of ice, simply shut off the warmth of an entire hemisphere? Or are we still only circling around the true trigger of the Younger Dryas, seeing patterns in water and ice without yet grasping the whole mechanism? If the freshwater hypothesis feels almost too neat, that is because it is. The Earth is not a single switch where one flood turns the system off. When scientists test this idea with climate models, some results support a conveyor collapse while others show only partial slowdowns. In some simulations, the 𝐓𝐈𝐌𝐿𝐄𝐒 weakens but does not fully halt. Europe still cools, but not always to the extent we see in the ice cores. That gap between model and evidence is where doubt enters. It reminds us that while meltwater is a powerful agent, the real climate machine has far more moving parts than our computer screens can easily capture. Another thread of evidence comes from the land downstream of those great ice-dammed lakes. In the Mackenzie Basin, geologists have mapped massive scours and spillways, giant features carved by torrents no ordinary river could produce. These are interpreted as mega-flood paths, signs that volumes of water once surged north at a pace impossible to imagine today. At the mouth of the St. Lawrence system, sediment fans also suggest abrupt pulses into the Atlantic. Each site tells part of the story, but they do not always agree on timing. Was it a single cataclysm or a stuttering sequence of smaller releases? That matters, because the Younger Dryas cooling was sharp, not gradual. One of the more intriguing puzzles is that the Younger Dryas was not the only cold snap during deglaciation. Similar events earlier in the last ice age also show fingerprints of freshwater disruption. These are the so-called Heinrich events, when armadas of icebergs carved into the North Atlantic and melted, freshening the surface. Those earlier episodes help frame the Younger Dryas as part of a pattern. Perhaps the climate system, already unstable, was primed to respond violently to even modest freshwater surges. In that sense, lake Agassiz may have been less the sole culprit and more the final straw in a chain of stresses. Still, for all its appeal, the freshwater idea raises another question. If the conveyor can be stopped so easily, why does it not happen more often in the paleoclimate record? Meltwater pulses occurred repeatedly as ice sheets retreated, yet not everyone left behind a millennium of cold. This inconsistency fuels healthy skepticism. It may be that only under very specific configurations of ice cover, solar input, and ocean circulation can a flood tip the system into full reversal. That makes the Younger Dryas both an echo of earlier events and a unique convergence. The freshwater hypothesis has not been discarded. It is still the first suspect because it draws on processes we know occurred: melting ice, draining lakes, and disrupted salinity. But even its strongest proponents admit it may not explain the entire picture. Other suspects, volcanoes, solar shifts, or even impacts, still wait in the wings. And so the narrative of the Younger Dryas remains unsettled. Did water alone undo the warmth of an entire hemisphere, or was the ocean conveyor just one gear in a larger, messier machine of abrupt climate change? That question, like the conveyor itself, continues to circulate without ever quite sinking. When people think about sudden cold spells in history, the finger often points skyward, not to comets, but to volcanoes. We know from more recent times that a single eruption can veil the planet in haze and drop global temperatures for a year or more. The eruption of Tambora in the year 1815, for instance, gave Europe and North America the infamous year without a summer. Crops failed, famines spread, and frost struck in June. That was a temporary hiccup compared to the Younger Dryas, but it shows how profoundly Earth's own voice can echo through the climate. So it is reasonable to ask whether the abrupt cooling that began around 12,900 years ago might have been triggered, at least in part, by a spasm of volcanism. One eruption in particular often stands at the centre of this debate: the Leyte Sea eruption in what is now Germany. This was not a minor venting, but one of the largest volcanic events of the late Pleistocene. Around 13,000 years ago, give or take a handful of decades, it blasted a column of ashen gas into the stratosphere and reshaped the Rhineland with a new caldera lake. Tephra from this eruption is found across Central and Northern Europe, a silent marker that archaeologists and geologists use to date sites with precision. The Leyte Sea eruption injected vast amounts of sulfur into the atmosphere, Sulfate aerosols scatter sunlight, cool the surface, and can linger long enough to affect seasonal cycles. Some researchers suggest this eruption alone might have delivered the first shove toward Younger Dryas conditions. But the timing is delicate. When ice cores from Greenland and Antarctica are examined, several sulfur peaks appear in the centuries bracketing the Younger Dryas onset. A recent reconstruction identified not just one eruption, but a cluster of at least 4 major volcanic events between 12,900 and 12,870 years before the present. These were not isolated puffs, but a concentrated episode of planetary restlessness. In that narrow window of just over a century, Earth seems to have been unusually active. Beyond Europe, other volcanoes were awakening. In what is now Japan, Sakurajima produced an eruption around the very cusp of the Younger Dryas. The deposits suggest it was among the most powerful in the history of that famously active island arc. In Iceland, the Katla system shows evidence of activity close to the same horizon, sending basaltic ash into the North Atlantic winds. In the Americas, the Andes contributed eruptions that may have added their own veil of aerosols to the skies. Even Antarctica has deposits that point to volcanic episodes in that same period. Taken together, these scattered sites suggest not one solitary eruption, but a global pattern of frequent activity just before and during the onset of the cold reversal. The climate mechanism is straightforward in theory. Volcanic aerosols lofted high into the stratosphere block incoming sunlight. The effect is strongest in the first 1 to 3 years, but with several eruptions close together, the cooling can persist or compound. The aerosols also alter atmospheric circulation, shifting wind belts and changing rainfall. When the North Atlantic is already sensitive, such perturbations could be enough to trigger or amplify a collapse in ocean overturning. In other words, volcanoes do not have to explain the Younger Dryas alone. They could have primed the system, nudging the conveyor to falter, with other processes sustaining the chill. Ice core data help build this picture. Sulfate spikes preserved in Greenland show multiple volcanic signals within the critical centuries. The cumulative sulfur load for this interval is higher than anything seen in the last 2 millennia of recorded history. That is remarkable, because even clusters like those that preceded the Little Ice Age did not rival this intensity. If sulfate burdens of that magnitude were real, the atmosphere may have been repeatedly dimmed, summer after summer, creating a climate primed for abrupt transition. Of course, the question remains whether such eruptions can explain not just a few cool decades, but a millennium-long return to glacial conditions. Here the evidence is less clear. Volcanic forcing alone typically fades within a decade. To stretch cooling across more than 1,000 years, volcanoes must have triggered feedbacks, perhaps disrupting the Atlantic circulation in tandem with meltwater pulses. In this view, volcanism was the spark, not the sustaining fire. The skeptics caution that volcanic signatures can be difficult to date precisely. Tephra layers in sediments sometimes shift, and sulfate spikes in ice cores may overlap with other signals. Without exact synchrony, it is challenging to say whether the eruptions coincided precisely with the start of the Younger Dryas, or merely occurred nearby in time. Yet even cautious voices admit the coincidence is striking. A cluster of large eruptions in the decades before, the cooling is not something we can easily dismiss, so we are left with a plausible second suspect. Volcanoes certainly darkened skies in those centuries, and their fingerprints remain in ice and ash. Did they tip the climate into chaos, or were they just one voice in a chorus of disruptions? Perhaps the Younger Dryas was not born of a single cause, but of Earth's internal restlessness, combining with fragile oceans and retreating ice. If so, the haunting question lingers. Did the ground beneath our feet, coughing sulfur into the sky, quietly script the coldest chapter of our species' early memory? One of the most thought-provoking aspects of this volcanic angle is how it forces us to think about the Earth as an interconnected system, rather than a set of isolated disasters. When we picture a major eruption, we often imagine a single violent day that reshapes the landscape. But volcanism can unfold in sequences, swarms of medium-sized eruptions that do not make global headlines but, strung together, leave a long shadow on climate. The research pointing to more than 30 eruptions in the 4 centuries before the Younger Dryas onset is a reminder that we may be dealing with cumulative pressure. A single Tambora-sized blast is catastrophic in its own right, but 3 or 4 such events within a century is something qualitatively different. It builds an atmosphere that never fully clears, a constant haze that might shave down growing seasons year after year. The archaeological record hints at this sort of environmental stress. In parts of Europe, pollen studies show woodlands retracting, replaced by more open grasslands in the generations after the Lacca Sea eruption. Whether this shift was entirely volcanic or mixed with cooling from other causes is debated, but the point remains that ecosystems were already under duress. Small swings in sunlight and rainfall could have amplified the strain. For people and animals living through it, the experience may have been one of summers that seemed shorter and winters that seemed just a little harsher, stacking unease onto unease until entire lifeways were reconfigured. Another clue comes from the chemistry of ice. Volcanic sulfate does not only cool the planet, it also interacts with ozone. Some modelling studies suggest that repeated eruptions could have thinned ozone layers in high latitudes, changing not just temperature but ultraviolet exposure. This is speculative, but if true, it would add another dimension to how volcanism might have stressed life during the Younger Dryas. It reminds us that eruptions are not merely local spectacles, they ripple upward into atmospheric chemistry in ways still being pieced together. Skeptics often counter that the precise dating of these eruptions remains fuzzy. Tephra shards in sediment cores are tiny and often reworked by rivers or winds. Ice cores tell us there were multiple sulfate spikes, but pinning them to exact volcanoes is like matching puzzle pieces with frayed edges. Still, the very presence of so many spikes within such a narrow window is compelling. Even if we cannot yet assign every eruption a name, the atmosphere itself records their presence. So when we ask whether the Earth coughed up the cold, perhaps the more accurate framing is that the planet was already breathing uneasily. The retreat of ice sheets lightened the crust, magma systems adjusted, and volcanism surged at precisely the moment when the climate was most sensitive. Did this chain reaction simply nudge a fragile system into a new equilibrium? Or did it slam the door on warming that might otherwise have carried us smoothly into the Holocene? That remains the open question, and it is one worth holding in mind as we follow the next suspects in this ongoing investigation of deep time. At a certain point in this story, the gaze of science shifted upward. If oceans and volcanoes could not fully account for the sudden shock of the Younger Dryas, perhaps the culprit was not of this Earth at all. Around the middle of the 2007 conference season, a group of researchers proposed what became known as the Younger Dryas impact hypothesis. The idea was stark and simple enough to make headlines. Something fell from the sky. A comet or an asteroid, possibly fragmented into multiple pieces, may have struck or exploded over North America roughly 12,900 years ago. The result, they argued, was a cascade of disasters, wildfires racing across landscapes, ice sheets destabilized by sudden heat, and ecosystems thrown into collapse. In this telling, the sudden return to cold was not just a quirk of the climate system, but the fallout of an extraterrestrial visitor. The attraction of this hypothesis is easy to see. Earth is no stranger to impacts. 66 million years ago, a large asteroid transformed the fate of dinosaurs and paved the way for mammals. That was a global catastrophe written in iridium layers in a crater on the Yucatan coast. If one impact could end the age of reptiles, might a smaller one have been enough to jolt the late Pleistocene? The idea taps into a narrative we already understand, that cosmic accidents have shaped life's history before, and they could have done so again in more recent memory. Proponents of the impact hypothesis argue that the Younger Dryas began too abruptly to be explained by slower earthbound mechanisms alone. Within just a few decades, they say, a warming world lurched back into glacial chill. They suggest that only an extraordinary trigger could set so many dominoes falling at once, firestorms consuming up to a tenth of the Earth's biomass, meltwater flooding oceans, and megafauna extinctions clustering suspiciously around the same window. Rather than a long build-up of stresses, the hypothesis paints a picture of a sudden hammer blow. From the outset, the proposal was controversial. It called not for subtle nudges, but for an abrupt shock, and the evidence was still fragmentary. Critics noted that no crater had been found, and that was awkward. Large impacts leave scars. The idea of a fragmented comet, exploding in the atmosphere rather than gouging the ground, was offered as a solution. Such events do not always leave obvious craters. The Tunguska explosion in Siberia in the year 1908 flattened forests across 2,000 square kilometres, yet left no crater behind. Perhaps the Younger Dryas began with something similar, but on a larger or more widely dispersed scale. This possibility opened a fresh line of debate. Was it more plausible that Earth's own feedbacks had stumbled, as they had many times before, or that a cosmic intruder had rewritten the script at the very moment warming seemed to be gaining ground? The hypothesis was bold, even cinematic. It resonated with a public imagination already primed by stories of dinosaur-killing asteroids and Hollywood films about planetary impacts. But bold ideas require extraordinary evidence, and that evidence has remained contested. To be clear, the impact hypothesis does not stand outside science. Its proponents are geologists, archaeologists, and climatologists publishing in peer-reviewed journals. They look for signals in sediments, anomalies in chemistry, and patterns in extinction. Yet the hypothesis has also become a lightning rod in the broader conversation about how science handles uncertainty. On one side are those who argue the evidence for an extraterrestrial trigger is mounting and deserves serious attention. On the other are those who caution that the Earth itself offers enough mechanisms to explain abrupt climate shifts without importing cosmic drama. For us, the point is not to resolve the debate, but to understand its stakes. The impact hypothesis offers a story where the Younger Dryas is not just another Dansgaard-Oeschger oscillation, not just another hiccup in ocean currents, but an event unique in its violence. If true, it would mean that our species entered the Holocene in the shadow of a disaster from the stars. If false, it still serves as a reminder of how fragile the climate system is, capable of tumbling into chaos from the inside out. And so the haunting question hangs above us. Was the coldest interruption of the last ice age written into the Earth's own rhythms, or was it imposed by something that fell without warning from the sky? If we let the thought experiment run further, it becomes clear why the impact hypothesis continues to attract attention, even when much of the scientific community remains cautious. There is something profoundly unsettling about the notion that, just as ice sheets were retreating and ecosystems were beginning to reorganize, a cosmic accident might have reset the trajectory. It would mean that the shift into the Holocene, the warm epoch in which all of recorded human history unfolds, did not arrive smoothly, but through a catastrophe that nearly derailed it. That narrative, even if unproven, changes how we think about fragility and contingency in our own past. To follow this idea, we have to imagine the scale of such an event. Advocates suggest not a single dinosaur-killer rock, but rather a swarm of smaller fragments. A disintegrating comet passing near Earth could scatter pieces across continents, each one releasing massive amounts of energy as it burned through the atmosphere or struck the ice sheets. The visual comparison is again Tunguska, magnified many times. Instead of flattening one forest in Siberia, imagine firestorms kindling across broad regions, soot and smoke rising into the atmosphere, and shock waves disturbing vast ice sheets already on the edge of instability. The climatic response in this view would have been rapid cooling, driven both by atmospheric particles blocking sunlight and by freshwater floods cascading into the North Atlantic. The proposal also has a way of tying together disparate mysteries. Why do we see widespread evidence of burning around the onset of the Younger Dryas in so many places, from North America to the Middle East? Why do some species of large mammals vanish around the same window, while others survive only in refuges? Why does the Greenland ice core show such an abrupt plunge into colder conditions? Each of these patterns can be explained in other ways, but the impact hypothesis offers a single dramatic trigger. That coherence makes it attractive to some researchers, even when the details remain unresolved. Yet coherence can be deceptive. Earth's climate history is full of abrupt changes, many of them lacking any cosmic explanation. Dansgaard-Oeschger events recurred dozens of times in the ice core record, showing that the system has its own capacity for sudden jumps. Megafauna extinctions, too, unfold at different times in different regions, hinting at a complex interplay of hunting, habitat change, and stress. Fires can be sparked by lightning, drought, or human activity without requiring a comet. To argue that an impact caused all of these at once risks compressing a tangled history into one clean storyline. And history, as we know, rarely obeys clean storylines. Another reason the impact idea lingers is psychological. Humans are primed to fear what comes from the sky. Ancient myths are filled with tales of fire from above, of stars falling, of celestial punishment. Modern culture, from disaster films to doomsday predictions, continues this theme. When scientists propose that such a thing really might have shaped the lives of our late Pleistocene ancestors, it resonates on a level deeper than data alone. That resonance is not evidence, but it explains why the idea has travelled so widely beyond specialist journals into popular imagination. For a moment, it is worth considering the counterfactual. Suppose the impact hypothesis is wrong. Suppose the Younger Dryas was simply another episode of Earth's chaotic system flipping between states. That would make our planet no less extraordinary. It would remind us that abrupt climate shifts can arise from within, without any cosmic trigger, and that they can arrive with little warning. In some ways, that lesson is even more relevant to the present. If Earth's own feedbacks can plunge us into thousand-year cold snaps, then the stability we take for granted today is more precarious than we might think. But if the hypothesis is right, then our story carries another weight. It would mean that Homo sapiens survived not only the instability of their own planet, but also the collateral damage of a cosmic accident. It would place our species in a lineage of survivors that stretches back through countless extinctions, marked this time not by the fall of reptiles, but by the disappearance of mammoths, mastodons and saber-tooths. In that case, the Holocene is not just a warm period we happen to inherit, but a fragile aftermath of disaster, a reprieve gifted by chance. The truth for now remains unsettled. Scientists continue to test sediments, model impacts, and argue in papers and conferences. Some of the fiercest debates are not about whether something happened, but about how evidence should be interpreted, calibrated, and reproduced. That is the ordinary grind of science, sometimes invisible to the public. What the Younger Dryas impact hypothesis illustrates is how much hangs on these slow, careful processes. A single anomaly can appear dramatic, but unless it is confirmed across methods and sites, it cannot carry the burden of a global catastrophe. And so we circle back to the haunting question. Was the sudden freeze at 12,900 years ago just another step in Earth's restless pattern? Or was it a scar left by a fragmented wanderer from the depths of space? We may not have the answer yet, but we do know this. Our ancestors endured either way. Whether the sky betrayed them or the oceans did, they adapted, they survived, and they passed the story forward, even if they never knew the script themselves. Archaeologists often stumble on patterns without knowing at first why they matter. In the late 20th century, teams working across the American West began to notice a recurring curiosity in their trenches. Beneath the topsoil, below layers of sand and loess, there appeared dark streaks of earth unlike anything around them. These bands were rich in organic matter, sometimes almost black against the pale sediments. They often marked marshy conditions or buried soils, and so they became known, informally at first, as black mats. What startled researchers as they catalogued these finds was how consistently they seemed to appear around a particular age, roughly 12,900 years ago. That was the very threshold of the Younger Dryas, the sudden return to Ice Age cold. At first, black mats were treated as markers of local environmental change. A marsh might have expanded, a groundwater table might have risen, or a river might have shifted course, leaving behind layers of silt and peat. Yet as radiocarbon dating improved, it became harder to ignore the temporal alignment. Sites hundreds of kilometers apart, from Arizona to Montana to the Dakotas, yielded black mats dated to the same moment. The coincidence called for explanation. Was it a regional quirk of hydrology, or was it evidence of something larger, perhaps even global in scale? One striking feature of these layers is their association with abrupt shifts in the record of animals. At the Murray Springs site in Arizona, a black mat lies directly above a bed littered with the bones of mammoths and other Pleistocene beasts. It is as if the dark soil sealed the end of an era, a geological bookend closing the chapter on megafauna in that region. Similar juxtapositions appear elsewhere, with bones of now extinct animals lying beneath, and the organic rich mat overlying them like a funerary shroud. Archaeologists, careful by nature, hesitate to declare cause and effect from such associations, but the pattern is haunting. Another characteristic is chemical. Studies of these mats show elevated levels of soot and charcoal, indicators of widespread burning. In some cores, the concentration of microscopic charcoal particles rises sharply at this boundary, suggesting that fires consumed large stretches of biomass. These were not ordinary campfires or even local wildfires. The scale implied by the data points to regional, even continental blazes. The skies would have darkened with smoke. Vegetation would have withered. For the animals and people who lived through it, the experience may have been terrifying, a world suddenly aflame. Still, we must be careful. Charcoal in sediments is not unusual. It can accumulate from many small fires over long periods. The challenge is proving synchronicity, that so many black mats really did form at the same time, not just within centuries of one another. Some researchers argue the calibration of radiocarbon dates is not precise enough to tie them all to 12,900 years ago. Others counter that the clustering is too tight to be coincidence. The debate continues, with each new site adding data but also complexity. Another clue comes from the types of plants preserved in these layers. Pollen analysis shows abrupt changes in vegetation at the same horizons. Grasses and sagebrush often replace woodlands, implying a drier, colder landscape. In that sense, the black mats are not only ashes but also records of ecological transition. They capture a moment when ecosystems were overturned, when forests shrank, wetlands spread, and familiar plant communities vanished. To the animals and humans depending on them, this would have meant sudden shifts in food and habitat, adding stress to populations already adapting to climate volatility. What remains uncertain is the trigger. Did the fires create the mats, or did shifting hydrology create wetland deposits that happened to trap charcoal from elsewhere? Were the mats cause, effect, or coincidence? Even their name hides complexity. Some are peaty, some are silty, some are truly burned. They're unified less by composition than by timing, and it is that timing that makes them so intriguing. When archaeologists kneel over a trench wall and trace a finger across a thin black stripe, they are touching a horizon that speaks of catastrophe. Yet the nature of that catastrophe is contested. Was it simply that climate shifted abruptly, drying forests into tinder? Was it that humans, hunting and clearing, sparked conflagrations beyond their control? Or was there some extraordinary event that ignited half a continent at once? These questions keep the black mats in scientific conversation decades after their discovery. Perhaps the most sobering thought is how thin these layers are. Sometimes only a few centimetres, sometimes no more than a stain, they represent upheavals that transformed landscapes and lives. In them lies evidence of burning, extinction, and survival. They remind us how fragile the record is, how easily a 1,000-year story can be compressed into a smudge of dark soil. The mats endure as puzzle pieces, waiting to be fit into the larger mosaic of the Younger Dryas. For now, they whisper rather than proclaim, hinting at fire and loss, daring us to ask whether Earth itself or something beyond it struck the match. Some of the most compelling discussions about these enigmatic horizons come from comparing sites far beyond the North American plains. Researchers working in South America, the Middle East, and even parts of Europe have described similar layers that appear at the cusp of the Younger Dryas. While not identical in character, they often share that darkened, carbon-rich profile that suggests fire or rapid ecological turnover. This wider distribution raises the possibility that what archaeologists first labelled black mats in Arizona might not be an isolated regional signature, but part of a much broader global pattern. At Arlington Canyon on California's Channel Islands, for example, the soil profiles reveal an abrupt shift toward darker organic-rich sediments that coincide with faunal losses in the region. Farther afield, cores from Chile and Venezuela show charcoal peaks at the same approximate age. The implication is that fire was not just a local disturbance, but one that touched multiple continents. Of course, linking these layers precisely in time remains difficult. Radiocarbon dating is powerful but imperfect, and the calibration curves required to translate dates into calendar years add uncertainty. Still, the convergence is striking enough that it cannot be dismissed as mere coincidence. Another angle of study involves what lies immediately above and below the black mats. Beneath them, soils often contain traces of rich faunal communities, mammoth bones, camel remains, or other megafauna that vanish from the record soon after. Above them, by contrast, sites show evidence of a new ecological order, with smaller animals, altered vegetation, and in some cases human toolkits that suggest different survival strategies. The mats thus seem to mark not just an environmental threshold but also a cultural one, a line across which both nature and humanity were forced to adapt. Critics, however, urge restraint. They point out that organic rich layers can form for many reasons: wetter conditions, ponding of water, or simple accumulation of decayed plant matter. In some places, the mats may owe more to hydrology than to fire. This has led to sharp disagreements over whether they should be interpreted as signatures of catastrophe at all. For some scientists, they are merely markers of shifting groundwater during a cooler climate, no more mysterious than a buried marsh. For others, their timing and associations are too consistent to be brushed aside. Perhaps the best way to think about the black mats is as silent witnesses. They do not tell us exactly what happened, but they anchor us to a moment when the world changed. Whether born of fire, flood or frost, they embody the disruption that defined the onset of the Younger Dryas. When we place them in the broader puzzle, alongside ice core records, pollen shifts and the disappearance of great animals, they remind us that history can leave its signature in the thinnest of lines. The haunting question remains: do these dark streaks preserve the memory of ordinary earthly processes, or do they whisper of an extraordinary event that reshaped life on a planetary scale? If dark soils and charcoal hinted at catastrophe, it was the discovery of microscopic crystals that truly ignited debate. Beginning in the early 2000s, teams analysing sediments from around 12,900 years ago started reporting the presence of exotic materials: grains of glassy melt, spheres of fused minerals, and even carbon structures so small they qualified as nano-diamonds. To the trained eye, these were not ordinary products of fire or erosion. They appeared to be formed under conditions of extreme pressure and temperature, the sort of forces that nature does not casually produce on Earth's surface. The suggestion was clear, though controversial. Perhaps something had fallen from the sky. Nano-diamonds are among the strangest of these proxies. They are diamonds, yes, but not the glittering gemstones we imagine in jewellery. They are crystals only billionths of a metre across, too small to see without an electron microscope. On Earth, such structures are known to form in a few contexts. They can appear in meteorites, forged in the violent birth of the solar system. They can also be created during hypervelocity impacts, when shockwaves compress carbon into diamond in the blink of an eye. Finding them at a sediment boundary, then, invites the question of whether a similar impact occurred locally. Melt glass tells a parallel story. These are shards of silica and other minerals that show evidence of having been liquefied at extremely high temperatures and then cooled rapidly. In laboratory experiments, such textures can only be reproduced under conditions far beyond what wildfires or volcanism usually achieve. Some samples from sites in North America have been estimated to require heating above 2,000 degrees Celsius, hotter than basaltic lava, and in the realm of impact fireballs. Their chemistry often shows unusual mixes of terrestrial and extraterrestrial elements, as though local soil was briefly fused with cosmic material. Microspherules add another layer. These tiny rounded droplets, often of iron or silica, look like miniature beads of glass. They are thought to form when material is vaporized, and then condenses as it cools while falling back through the atmosphere. They are abundant in sediments at known impact sites such as the Cretaceous-Paleogene boundary, the layer associated with the extinction of the dinosaurs. When similar spherules were reported in Younger Dryas boundary layers, it sparked immediate comparisons. Could this be a smaller cousin of the catastrophe that ended the reign of reptiles? Yet as with so much in this story, the interpretation is contested. Critics point out that nano-diamonds are extremely difficult to identify reliably, and not all laboratories have replicated the findings. Some of the reported structures may be other carbon phases misclassified. Melt glass, too, can form in volcanic eruptions or lightning strikes, though usually in much smaller quantities. Microspherules can arise from industrial processes, though of course no factories existed in the late Pleistocene, which complicates but does not invalidate the comparison. The debate often comes down to context. Are these proxies truly synchronous and widespread, Or are they local oddities magnified by selective sampling? Despite these disagreements, what makes these particles compelling is their convergence. At dozens of sites, from Pennsylvania to Syria, investigators have reported some combination of nano-diamonds, melt glass, or spherules at horizons dating to the Younger Dryas onset. Each type alone might be ambiguous. Together they paint a picture, at least to some scientists, of an event involving intense heat, shock, and airborne debris. The scale of that event remains uncertain. Was it a swarm of cometary fragments raining down, a single large airburst, or perhaps a rare earthly phenomenon still poorly understood? What remains undeniable is that the microscopic world offers a new lens on prehistory. Where bones and pollen tell us about living communities, these crystalline proxies record physical processes of unimaginable violence. They remind us that history is written not only in fossils and tools but also in atoms shocked into strange forms. Each shard of glass, each nano-diamond is a clue from a moment when normal processes faltered and extraordinary forces briefly took control. And so, we are left with the question, do these tiny crystals testify to fire from the sky? Or are they misread whispers of more mundane origins? The samples sit in laboratories, viewed through electron microscopes, their meaning fiercely debated. We may not yet know whether they are relics of catastrophe or curiosities of geology, but their presence ensures that the Younger Dryas remains one of the most intriguing and unsettled mysteries in the story of climate and life. One of the striking things about these proxies is how they challenge our sense of scale. When most of us picture evidence of catastrophe, we imagine massive craters, toppled forests, or shattered coastlines. Yet here the debate revolves around particles so small they fit comfortably on the head of a pin, invisible to the naked eye, requiring specialized instruments to detect. That alone makes the case difficult to resolve. A mammoth bone can be dated and held in a museum drawer. A microdiamond has to be carefully isolated from ordinary carbon, its lattice measured atom by atom to distinguish it from lookalikes. Each laboratory step carries the risk of contamination, misinterpretation, or disagreement. The story of these proxies is as much about the challenge of measurement as it is about what truly happened 13,000 years ago. Consider the controversy over Nano-Diamonds, a hexagonal form of diamond that some groups have claimed to find in Younger Dryas sediments. Nano-Diamonds is famous because it can form under the extreme shock pressures of meteorite impacts. Its very presence would be a smoking gun. Yet subsequent studies have questioned whether these crystals are genuine or instead misidentified graphene structures produced by heating carbon. Here we see the limits of analytical certainty. A single electron microscope image can look convincing, but the interpretation may hinge on subtle differences in diffraction patterns, with different labs arriving at opposite conclusions. Science, in this sense, is not only a search for truth, but also a dialogue between methods, where the reliability of each instrument and protocol is tested. Melt glass tells a similar tale of complexity. While some samples exhibit chemical ratios consistent with terrestrial soil fused with cosmic dust, others more closely resemble volcanic byproducts. Distinguishing between these sources requires careful analysis of trace elements like chromium, nickel, or iridium, and even then the picture can be cloudy. A shard that looks extraordinary under one test might turn out ordinary under another. The uncertainty frustrates those who hope for a simple answer, but also underscores the need for humility. Nature has more ways to make strange materials than we often assume. Despite the uncertainties, it is fair to say these proxies have pushed the conversation forward. Before their discovery, the Younger Dryas was largely framed as a puzzle of ice, oceans, and gradual climate cycles. With the addition of nano-diamonds, melt glass, and spherules, the possibility of a sudden, high-energy trigger entered the debate. Whether or not that trigger proves to be extraterrestrial, the mere act of exploring these particles has broadened the range of hypotheses and forced researchers to refine their methods. In this sense, even contested evidence serves science, not by resolving questions but by sharpening them. And so, staring at these microscopic witnesses from the deep past, we are left with an oddly human dilemma. Do we trust the glitter of the tiniest diamonds, the smooth beads of frozen droplets, the shards of glassy melt, enough to rewrite the story of an entire epoch? Or do we file them away as curiosities, intriguing but insufficient to bear the weight of global catastrophe? Until consensus emerges, the particles remain suspended between possibilities, ordinary in size, extraordinary in implication, and forever tied to that abrupt winter which began 12,900 years ago. It is not often that a single element can stir decades of debate, but platinum has managed exactly that. Deep within the Greenland ice sheet, in a layer dated to roughly 12,822 years ago, researchers noticed a sudden and dramatic rise in platinum concentration. The discovery came from the 𝐓𝐈𝐌𝐄𝐒 ice core, a frozen time capsule drilled down more than 3 kilometers, preserving annual snowfall compacted into neat layers of history. In this vast vertical library, each thin band is a year, sometimes even a season, offering a chemical fingerprint of Earth's atmosphere at the moment the snow first fell. In most of the record, platinum hovers at barely detectable levels, its presence modest and consistent. But at this one point the curve shoots upward, forming a spike that seems to shout across the millennia. Platinum is not an element we expect in abundance on the surface of the Earth. It is rare, precious, and usually found in trace quantities. When it suddenly appears in larger amounts, geologists raise their eyebrows because there are only a few known sources that can explain it. One possibility is an influx of cosmic material, because many meteorites carry higher proportions of platinum group elements than our crust normally contains. Another is volcanic activity, since certain eruptions can dredge platinum from deep within the mantle and loft it into the stratosphere. What made the GISP2 spike so intriguing was not only its scale, but also its timing. It arrived just after the onset of the Younger Dryas cooling, aligning closely with the period of upheaval we are trying to explain. Comparisons with volcanic signals provided both clarity and confusion. In the same core, a massive sulfate spike clearly marks the eruption of the 𝐓𝐿𝐄𝐒𝐒 volcano in Germany, dated to roughly 60 years earlier. Sulfate is a reliable volcanic proxy, produced in abundance when sulfur-rich magma meets the atmosphere. The platinum spike, however, stands apart. It is offset in time from the 𝐓𝐿𝐄𝐒𝐒 layer, and lacks the corresponding sulfur signal we would expect if it too were purely volcanic. In other words, it is platinum-rich but sulfate-poor, hinting at a different source. This leads us to the problem of fractionation, the odd distribution of platinum compared to its geochemical siblings. In meteorites, platinum usually travels with iridium, another platinum group element. The two are famously paired in the thin clay band that marks the end of the Cretaceous, deposited when an asteroid struck the Yucatan and ended the reign of the dinosaurs. Yet in the Greenland ice, iridium remains conspicuously low. Platinum stands tall, while iridium barely stirs. How do we account for this imbalance? Some argue that the impactor must have been unusual, perhaps an iron-rich body with an odd elemental ratio. Others suggest that post-depositional processes, how particles settle, travel, or are preserved in snow, could separate one element from another. But neither explanation is fully satisfying. The spike also raises questions of transport. For platinum to arrive in Greenland ice, it had to be carried high into the atmosphere, distributed across long distances and deposited through snowfall. That requires an energetic source, something more dramatic than a small local fire or isolated volcanic plume. Yet it does not fit neatly with our catalogue of known impact markers. It stands as a kind of chemical orphan, too unusual to be comfortably volcanic, too irregular to be a textbook cosmic signature. What then does the platinum tell us? It tells us that something unusual happened around 12,800 years ago, something capable of lofting exotic material into the northern skies. Whether that something was the fragmentation of an incoming body, an unrecognized volcanic event, or a process we have not yet imagined remains uncertain. The ice does not reveal its secrets easily, but the spike is there, etched into the frozen archive, a puzzle piece we cannot ignore. And so, the haunting question lingers. Is this platinum the fingerprint of a visitor from space, or the echo of Earth's own restless depths? The discovery of the platinum anomaly also highlights how ice cores are not just passive records of snowfall, but dynamic archives of global processes. Each layer traps not only gases and isotopes, but also microscopic dust, volcanic ash, and trace metals delivered from faraway sources. For platinum to be visible at all in such a record, the influx had to have been extraordinary compared to background levels. Researchers calculated that the concentration at the anomaly was more than 100 times higher than the average baseline. That makes the layer stand out like a flare in an otherwise quiet night sky. In a record extending back tens of thousands of years, this level of enrichment is almost unique. To appreciate the significance of this spike, it helps to look at the broader geologic context. Platinum belongs to a family of elements that tend to sink deep into Earth's core during planetary differentiation. That is why the crust is so poor in them. In contrast, meteorites, which preserve the primitive chemistry of the early solar system, often contain platinum in far greater proportions. Whenever we see a sudden enrichment in surface sediments or ice, it naturally tempts scientists to think of extraterrestrial delivery. This line of reasoning is part of what made the platinum discovery so attractive to proponents of the Younger Dryas impact hypothesis. They saw it as a potential analogue to the iridium spike at the Cretaceous-Paleogene boundary. But the comparison is imperfect. The dinosaur-ending event left behind a global, unambiguous signal, visible in marine sediments, lake deposits, and continental sections alike. The Greenland platinum spike, by contrast, so far appears more localized, without an equally clear counterpart in other cores or sediments. Its uniqueness is both its strength and its weakness. On one hand, it is a distinct marker, precisely dated within a narrow window. On the other, it lacks the global distribution that would make it indisputable as evidence of a large, extraterrestrial event. The fact that it stands alone forces us to question whether local processes in the Arctic atmosphere, or even in the snowpack itself, could have concentrated platinum in unexpected ways. Volcanology provides another interpretive path. While the Leacher Sea eruption is ruled out as the direct source, other less well-characterized eruptions may have occurred in the same time frame. Many volcanoes, especially subglacial or submarine ones, leave ambiguous signatures. Some can release trace amounts of platinum without producing the massive sulfate spikes that normally identify them. The difficulty is that the geochemical fingerprint of platinum from volcanic gases is not as well studied as that from meteorites. This gap in our knowledge leaves open the possibility that the Greenland anomaly represents a volcanic mechanism we do not yet fully understand. Another consideration is atmospheric circulation. Greenland sits in a region where air currents can funnel materials from both North America and Eurasia. A platinum-rich input from one continent could, in theory, have been captured and magnified in the snow record of a single site. This reminds us that an ice core is not a perfect mirror of the entire planet, but a regional sample with global hints. Any interpretation must balance local and global scales carefully. Ultimately, the platinum anomaly illustrates the broader challenge of the Younger Dryas puzzle. Every piece of evidence seems to contain both promise and ambiguity. The spike is real, measured repeatedly and robustly. Its timing coincides with a dramatic climatic transition. Its composition is unusual, not easily explained by ordinary Earth systems. Yet its singularity, its lack of accompanying iridium, and its absence in other well-studied cores prevent it from becoming the decisive proof that many hope for. Instead, it occupies a liminal space between certainty and speculation. What we can say with confidence is that around 12,800 years ago, something injected a burst of platinum into the atmosphere over Greenland. The ice has preserved that event faithfully, waiting for us to read it. Whether we eventually connect it to a comet, an unusual eruption, or a process still unknown, it is a reminder of how incomplete our understanding remains. The Earth's climate history is written in precious metals as well as in ice and bone, and sometimes even the rarest of elements can become a messenger from a forgotten past. When the Greenland ice first revealed its strange platinum signal, many wondered if the same anomaly might be found elsewhere, buried in other archives of Earth's deep past. One of the most ambitious attempts to answer that question has come not from the sky or from ice, but from the sea. In 2023, a team led by Christopher Moore reported on a series of sediment cores drilled from the bottom of Baffin Bay, the frigid stretch of water that lies between Greenland and Canada's Baffin Island. It is not an obvious place to look for traces of a cosmic event, yet the logic is sound. sediments that settle in the quiet depths of the ocean can remain undisturbed for thousands of years. Layer upon layer of silt, dust and microfossils accumulates, forming a natural stratigraphy not unlike the rings of ice or the bands of a tree. If an extraordinary event once rained unusual particles across the high latitudes, there is a chance that the ocean floor quietly caught and preserved them. The Baffin Bay cores were chosen carefully. They came from depths ranging between 500 and 2,400 metres, far beyond the reach of fishing trawlers, shipping traffic or industrial runoff. That detail matters because earlier studies of supposed impact markers had been criticised for possible contamination. Microscopic spheres of metal or glass, for example, could just as easily come from welding slag, fly ash, or other byproducts of modern industry. By venturing into these remote and pristine sediments, the researchers sought to minimise that risk. They were essentially going to one of the last places on Earth where human fingerprints could not easily be mistaken for cosmic ones. What they found was a series of distinct peaks in the abundance of microspherules, tiny rounded grains, often rich in iron or silica, shaped by rapid melting and cooling. Under the microscope, some showed aerodynamic forms, elongated or hollow as if frozen mid-flight. A few even displayed the so-called soccer ball texture, a lattice of polygons formed when molten droplets solidify at high speed. Alongside the spheres were shards of melt glass and metallic particles with unusual chemistry. Some grains carried a high nickel content, others showed iron combined with very low oxygen. These are traits that, in many cases, overlap with cosmic dust or cometary material. The signal was not overwhelming. Most of the spheres appeared to be terrestrial in origin, but the coincidence of their peak abundance with the onset of the Younger Dryas was difficult to ignore. If this had been the only study of its kind, it might have been dismissed as another anomaly. But the team emphasised how well preserved their samples were. The sediments were finely laminated, meaning the layers had settled undisturbed year after year, with little mixing by currents or burrowing animals. Radiocarbon dates from organic fragments allowed the team to build a reliable depth-age model, aligning each centimetre of core with a window of history. By this method, they could pinpoint the horizon that corresponded to roughly 12,900 years ago. It was there that the spikes in microspherules and melt glass stood out most clearly. Still, as with all lines of evidence in this debate, the interpretation is not straightforward. Critics point out that microspherules are not unique to cosmic impacts. They can form in volcanic eruptions, in lightning strikes, even in intense wildfires. The chemical analyses, while suggestive of a high-temperature origin, are not conclusive. The abundance peaks too were not confined to a razor-thin boundary but stretched across several centuries, blurring the neatness of the story. One might expect a sudden, singular event to leave a sharper mark. Instead, the cores tell a tale of elevated but variable signals. Was this the fingerprint of a comet breaking up in the atmosphere? Or is it a signature of Earth's own fiery processes at a time when glaciers were melting, volcanoes were restless, and ecosystems were under stress? The Baffin Bay results add weight to the cosmic hypothesis, but they do not settle it. What they do show, unambiguously, is that something unusual was happening in the North Atlantic around the time the Younger Dryas began. Tiny droplets of glass and spheres of metal born in furnaces of extreme heat found their way to the ocean floor. They remain there still, silent witnesses to a moment of upheaval. Whether those furnaces were in the heavens or within the Earth itself is a question that science continues to wrestle with. And perhaps that is the larger lesson. For every new core drilled, for every new particle measured, the mystery deepens even as the evidence grows. We are left with the haunting possibility that the truth may not lie neatly in a single cause, but in the entanglement of many, with sea and sky conspiring to reshape the course of human history. What makes the Baffin Bay discovery even more compelling is the broader geographic setting. This region lies at the gateway where Arctic waters mix with the North Atlantic, a crossroads of climate and circulation. If unusual material was falling through the atmosphere, this is exactly the kind of basin that would capture it efficiently, locking particles into fine-grained sediments that trickle down continuously from the surface waters. Oceanographers often describe such sites as natural sediment traps, and here the trap seems to have snapped shut right as the Younger Dryas began. That coincidence alone has forced researchers to ask whether the cores are preserving local fallout or echoing a much wider dispersal event. To test the origins of these particles, the team went beyond visual inspection. They employed scanning electron microscopy and energy dispersive spectroscopy, methods that allow them to map the elemental makeup of each grain at micrometer scales. What emerged was a picture of extremes: tiny droplets that had cooled so rapidly they froze into glass, metallic spherules containing nickel far above crustal averages, and microfragments with magnetism out of proportion to their size. Such features are difficult to reproduce in everyday terrestrial conditions, although they are not impossible. Lightning strikes in sandy soils, for example, can generate glassy fulgurites, and volcanic vents can eject metallic-rich ash. Yet the quantity, diversity, and timing of the Baffin Bay grains suggest more than random coincidence. Still, the story is not one-sided. Some geochemists argue that meltwater flooding during deglaciation could have mobilized sediments, reworking older material into younger layers and producing the illusion of a singular event. Others caution that without parallel cores from distant basins, it is premature to label the anomaly global. If only one region shows the signal, then perhaps it reflects a local phenomenon, a volcanic eruption, an ice-dammed lake bursting, or even processes at the glacier-ocean interface. These competing interpretations show how delicate the balance is between bold hypothesis and cautious evidence. One fascinating angle is how the Baffin Bay findings have reopened old debates about just how messy the Earth system can be. If spheres and glass are indeed impact proxies, then they reinforce the idea of a fragmented body scattering across the northern hemisphere, raining down debris and pulses rather than in a single clean layer. If they are not, then they push us toward explanations that involve the Earth's own turbulence, where volcanism, ice collapse, and ocean currents interact in ways we still struggle to model. In either case, the presence of such exotic materials in sediments so carefully dated to the critical threshold of 12,900 years ago ensures that this site will remain a touchstone in the ongoing search for answers. The seafloor has no voice, yet through these cores it seems to whisper a question back to us. Did the heavens truly fall, or are we mistaking the Earth's own restlessness for signs of catastrophe? Until we place these Baffin Bay records alongside a wider network of cores from other oceans, that question will remain open, lingering like the cold winds that swept across the North Atlantic at the dawn of the Younger Dryas. The story of Abu Hureyra begins not with cosmic fire, but with riverbanks and reeds. Perched above the Euphrates in what is now northern Syria, it was a small village of mud-walled huts, woven mats, and hearths, where families ground wild cereals and roasted gazelle meat. Archaeologists first uncovered it in the 1970s, racing against the floodwaters of the Tabqa Dam project. The rescue excavation produced tens of thousands of artifacts and samples that would later transform our understanding of early agriculture. Yet, at the time, no one suspected that the tale of Abu Hureyra might also conceal a record of a cataclysm. That realization came decades later, when sediments from the site were revisited with new eyes and new techniques. At a certain depth, corresponding to roughly 12,800 years ago, excavators had noted a curious blackened layer filled with charcoal, soot, and splintered building material. For years it was interpreted as a fire horizon, perhaps the remains of huts accidentally burned. But reanalysis revealed more. Grains of quartz displaying the kind of microscopic fractures usually formed only under enormous shock pressures, spherules of glassy material fused in ways that suggested flash melting, and anomalous concentrations of platinum far above local background levels. Together, these features hinted at conditions far more violent than domestic fire or routine accident. Supporters of the Younger Dryas impact hypothesis seized on Abu Hureyra as a key data point, because here was a human settlement sitting directly at the boundary. Unlike ice cores or deep-sea sediments, this was not a passive recorder of climate. These were the floors where people had knelt, the hearths where grain was parched, the plaster surfaces where children might have played. If strange debris rained down from the sky at the onset of the Younger Dryas, the villagers would have seen it, smelled it, perhaps fled from it. Even if their voices are gone, the debris locked into the site may still testify. The presence of shock-fractured quartz was particularly provocative. Such deformation patterns require pressures akin to those generated by large explosions or impacts. Critics counter that localized high-heat processes, including intense house fires, can sometimes mimic such textures. Yet the sheer abundance and distribution of the quartz grains, mingled with microspherules that cooled from molten droplets, suggested a phenomenon larger in scale than a cluster of burning huts. The platinum anomaly added another puzzle piece, linking the stratum to the same signature seen in Greenland ice and in several North American sites. Could a single widespread event have deposited this unusual mix across continents? That remains debated, but the correlation is difficult to ignore. Abu Hureyra also invites a deeper question. This was one of the earliest villages to experiment with the deliberate cultivation of cereals. The wild rye collected and parched here shows signs of transition toward domestication, a step that would eventually anchor the Neolithic revolution. What if this experimentation was not simply gradual progress, but a response to crisis? If sudden climate cooling devastated wild stands and forced foragers to secure food in new ways, then the seeds of farming may quite literally have been sown in the ashes of catastrophe. This does not mean an impact caused agriculture, but it does mean the Younger Dryas was part of the crucible in which farming emerged. Skeptics remain unconvinced. They note that Abu Hureyra's sediments are complex, disturbed by construction, erosion, and later occupation. Separating a singular global event from the messy realities of village life is not easy. Could platinum have arrived via dust storms? Could quartz have fractured in other ways? Could the melt droplets have been volcanic in origin? Each possibility has been raised and none can be dismissed outright. This is the constant tension in science, how to distinguish extraordinary evidence from ordinary processes when the past refuses to hand us clean experiments. Yet whether or not Abu Hureyra preserves the fingerprint of a cosmic visitor, it undeniably preserves the story of human resilience. Here, families endured one of the sharpest climatic reversals of the late Pleistocene. They lived through frosts that shriveled harvests, droughts that parched herds, and fires that scorched dwellings. In that struggle, they began to tinker with plants, to scatter seed intentionally, to select stronger stalks. Out of hardship grew a new way of life. That fact alone ensures Abu Hureyra remains central to our story, even if the question of falling skies is never resolved. And so the tell rises above the plain, now drowned beneath a reservoir, its secrets locked away. The grains of quartz, the flecks of glass, the anomalous platinum, each whispers of something extraordinary 12,800 years ago. Whether that was the roar of an airburst, the glow of volcanic fallout, or simply the Earth's own shifting rhythms, we may never know with certainty. But the people of Abu Hureyra knew something happened. Their lives bore the mark of it, and their descendants carried forward a new relationship with the land. That may be the most profound legacy of all. The deeper one looks at Abu Hureyra, the more it becomes clear that this single site is not just a local story, but a meeting point of global narratives. When the excavators in the 1970s hauled baskets of soil out of the trench, they were mainly concerned with saving an endangered record of the first farmers. Yet tucked within the fine silts were particles so small that no one at the time could have imagined their importance. Only decades later, under electron microscopes, did those grains reveal a record of extreme forces. What makes this particularly striking is that the transition recorded here, from broad-spectrum foraging to cultivation, lines up almost exactly with the onset of the Younger Dryas. It is as if the village itself stands at a hinge in human history, one where environment and culture lock together in a feedback loop of necessity and invention. There are subtle clues that the shift may not have been voluntary. Analysis of rye grains from before and after the cooling shows changes in size and resilience. Some plants appear to have been deliberately chosen for their ability to withstand shorter growing seasons and colder nights. Such choices imply an environment that was less forgiving, where relying on wild harvests alone became increasingly risky. In that sense, the unusual debris in the boundary layer, whether cosmic, volcanic or otherwise, serves less as an answer and more as a backdrop to a human drama of adaptation. Researchers also note that the fire horizon at Abu Hureyra contains not only melted materials but also unusual distributions of animal bone fragments, many of them cracked and burned. This has sparked debate. Was the site destroyed suddenly, forcing abandonment, or was it more of a repeated cycle of burning, rebuilding, and continued use? The truth may be somewhere in between. Villages on unstable floodplains often face disasters, whether caused by climate, accident, or conflict. Yet the combined presence of shock features, glassy spherules, and high-temperature residues has led many to argue that this was no ordinary episode of house fires. Adding to the intrigue is the fact that Abu Hureyra is not alone. Other Near Eastern sites dating to this same narrow window also show layers of disruption, though not all have been examined with the same intensity. If more were studied, would we find similar microscopic signals? Or is Abu Hureyra unique simply because its rescue excavation captured such an unusually thick archive? These questions keep the debate alive and remind us how much is left unexamined beneath the soils of the Fertile Crescent. What seems clear is that Abu Hureyra embodies a moment of cultural pivot. The people who lived there were forced to renegotiate their relationship with the land in the face of sudden climatic instability. Whether or not a comet flared in the sky above them, they adapted. They carried forward techniques that would spread across the Levant and in time reshape the human journey. In this sense, the site is less about proving or disproving a single hypothesis, and more about understanding how humans respond to crisis. The strange particles locked in its layers may point to extraordinary forces, but the seeds buried alongside them point to an even more extraordinary response: survival through innovation. If the Younger Dryas really did begin with something falling from the sky, then the most obvious question anyone can ask is also the simplest. Where is the hole? Large impacts leave large craters, visible for millions of years, yet at the transition into the Younger Dryas, we have no obvious smoking gun. This absence of a clear impact site has become one of the strongest criticisms of the cosmic hypothesis, because in the popular imagination, every story of fire from the heavens ends with a massive pit in the ground. The problem is that Earth's surface is not a static canvas. It is dynamic, covered by oceans, ice, vegetation, and shifting sediments. A crater could form and be erased, concealed, or left buried beneath kilometers of water or ice. Still, the lack of one visible and datable to around 12,900 years ago leaves a gap that no amount of microscopic debris can completely fill. For a while, attention turned to Greenland, where radar surveys revealed a circular depression beneath the 𝐓𝐈𝐌𝐿𝐄𝐒𝐒 Glacier in northwestern Greenland. When this feature was announced in 2018, the headlines almost wrote themselves, "A hidden impact crater beneath the ice sheet," perfectly positioned near the North Atlantic, exactly where a cosmic strike might destabilize ocean circulation. Yet the excitement faded quickly, as dating efforts showed the structure was far older than the Younger Dryas, possibly hundreds of thousands or even millions of years old. The 𝐓𝐈𝐌𝐿𝐄𝐒𝐒 crater may indeed be an impact scar, but it is not one that can be tied to the sudden chill of the late Pleistocene. That disappointment illustrates the difficulty of relying on craters alone. If the hypothesized impactor was a fragmented comet or a loosely bound asteroid, it may have exploded in the atmosphere in what scientists call an airburst. The Tunguska event in Siberia in 1908 is often cited as an example. A space rock detonated above the taiga with the force of a nuclear weapon, flattening 80 million trees across 2,000 square kilometers, yet leaving no crater. If something similar occurred over the Laurentide ice sheet or another icy landscape at the end of the Pleistocene, the energy release could have been immense, but the surface scar might be absent or short-lived, erased by ice flow, meltwater, and subsequent glaciation. Even a direct strike onto an ice sheet poses problems for crater hunters. Imagine an iron-rich body slamming into ice more than a kilometre thick. The transient crater might be swallowed almost immediately, filled by collapsing ice walls, then bulldozed and smoothed by centuries of glacier flow. Instead of a lasting depression, the record would be subtle. Disturbed layers in the ice, unusual melt channels or debris fields dispersed downstream. Those traces would be far harder to identify than the iconic ringed basins we see on the Moon or Mars, where erosion is minimal. Others point out that the vast majority of Earth's surface is ocean, and an impact in deep water would leave only fleeting signs. The waves and vapour plumes would be catastrophic for life nearby, but the crater on the seafloor might collapse within hours or be masked by sediments within centuries. Without a dedicated seafloor survey timed perfectly, such a feature could remain undiscovered. If the Younger Dryas was triggered by such an ocean strike, we may never find more than scattered geochemical whispers carried by currents and deposited into cores. This is where the debate becomes more philosophical than physical. Should we expect to find a crater? Some argue yes, because a bolide large enough to alter hemispheric climate must leave some trace. Others argue no, because the conditions at the time, ice sheets covering millions of square kilometres, dynamic oceans and shifting landscapes, were the worst possible for preserving a classic impact scar. Both positions are difficult to prove or disprove without more evidence. The absence of a crater, then, remains both a weakness and an open door. It weakens the argument for a single, massive, iron-rich meteorite striking Earth at precisely the right moment. Yet it leaves room for more complex scenarios. Multiple fragments arriving in sequence, atmospheric detonations scattering debris, or smaller impacts onto ice and ocean whose scars vanished. The question lingers not because it has a neat answer, but because it is one of those puzzles that resist closure. When we look up at the night sky and see the craters etched across the moon, it is easy to forget that Earth is no less bombarded, only more restless, more erosive, more alive. Perhaps the Younger Dryas crater lies buried beyond our reach, or perhaps there never was one, and the story must be written without that expected hole. The search for a Younger Dryas crater often reveals more about our expectations than about the Earth itself. We like clean cause and effect stories, a rock from the sky, a blasted hole in the ground, and a sudden shift in climate. Yet nature is rarely that neat. Even on Earth today, smaller impacts happen more often than many people realise. Most are recorded only by satellites as streaks of light or atmospheric flashes. They leave no craters at all. It is possible that 12,900 years ago the planet experienced something catastrophic by human standards, but geologically subtle, an event that left debris and fire but not the tidy bowl we instinctively imagine. There is also the uncomfortable reality of preservation bias. Our surviving craters tend to be in deserts, shield rocks, or other geologically stable places where erosion is slow. But much of the northern hemisphere at the end of the Ice Age was anything but stable. Huge ice sheets advanced and retreated, rivers roared with meltwater, and sea levels were rising. Even if a Younger Dryas impact made a crater, those forces could have erased it quickly. The very dynamism that makes Earth habitable also makes its impact record incomplete. Some researchers suggest we might need to broaden the definition of crater in this context. Instead of looking for a single obvious hole, we might expect to find disrupted ice flow patterns, buried layers of shocked debris, or chemical anomalies in sediments downstream. The signatures would be scattered rather than centralized. Imagine throwing a stone into a glacier. Instead of a neat splash, the result is hidden cracks, buried fractures, and displaced chunks of ice carried away in silence. The absence of a simple bowl in the ground does not mean nothing happened. It just means the surface response was complex. And then there is the possibility of scale. If the Younger Dryas was not triggered by one giant bolide but by a series of smaller fragments, then each individual strike might have been insufficient to leave a crater that survived to our time. A swarm of airbursts or small impacts could still generate widespread fires and atmospheric disturbance, enough to tip climate systems already on the edge. In that case, there never would have been a single dramatic scar, but rather a shower of ephemeral disturbances spread across continents. The question of the missing crater lingers like an echo in the wider debate. It challenges the impact hypothesis because it leaves us without the single piece of evidence everyone intuitively expects. But it also forces humility, reminding us that the Earth erases and hides much of its past, and that absence is not always disproof. If a comet did play a role in the Younger Dryas, we may never see its footprint in the way we want. The trail may remain a puzzle of scattered dust, fractured stones, and unanswered questions, and maybe the haunting question is the most fitting one. Do we need a crater to believe in an impact? Or do we need to let go of the idea that history always leaves behind the kind of traces we think it should? When the idea of a cosmic trigger for the Younger Dryas first began to gain momentum in the mid-2000s, much of the fascination came from exotic markers, microscopic diamonds, tiny glassy spheres, and mineral traces that looked like the fingerprints of an impact. These were the kinds of discoveries that could, at least in theory, offer hard proof that something violent and otherworldly had taken place. But science lives or dies on reproducibility. A single team reporting glittering nano-diamonds in a soil layer might be intriguing, but until other laboratories can find the same thing, using the same methods, the claim remains fragile. And this is where the Younger Dryas debate has so often become tangled in frustration. In the years that followed the first publications, independent teams around the world attempted to replicate the original results. Some reported success, identifying carbon spherules or structures consistent with high-energy heating. Others failed to find anything unusual at all. Even worse, blind tests in which sediment samples were distributed to different labs produced sharply contradictory conclusions. One group would identify an abundance of nano-diamonds in a layer dated to 12,900 years ago, while another found none, or found them in layers with completely different ages. Instead of convergence, the field began to fracture. This lack of consistency has fed accusations from all sides. Proponents of the impact hypothesis argue that subtle differences in preparation or electron microscopy settings can erase delicate structures, and that not all negative results are trustworthy. Critics counter that if the signal is so sensitive to technique, then it is not a reliable signal at all. At times the debate has grown personal, with claims of selective reporting, cherry-picking data, and even quiet hints of misconduct. To outsiders, this can look like scientists tearing at each other's throats, but it is also an inevitable part of testing radical ideas. Extraordinary claims attract extraordinary scrutiny, and the messiness is part of the process. The deeper problem is that the proxies themselves are ambiguous. Nano-diamonds can form in more than one way, not only through cosmic impacts, but also through industrial contamination, wildfires, or even laboratory artifacts. Microspherules can be produced in volcanic eruptions, lightning strikes, and campfires as well as impacts. Without robust statistical agreement across many sites and many labs, the extraordinary interpretation that all of these markers came from a fragmented comet remains on shaky ground. And yet, every year new papers appear, some presenting positive evidence, others finding none. The literature grows, but consensus remains elusive. This reproducibility war does not mean the hypothesis is wrong, only that the evidence is not yet persuasive to the broader scientific community. At the same time, it highlights how difficult it is to work with sediments that are tens of thousands of years old, buried, altered, and exposed to countless natural processes. Did the cosmic signal simply blur with time, or was it never there to begin with? That is the haunting question. One of the most striking episodes in this back and forth came when teams decided to submit the supposed impact proxies to blind trials. Sediment samples from sites in North America and Europe were mixed with control samples and handed over to laboratories with no labels. If the markers were real, and if they truly clustered at the Younger Dryas boundary, then the tests should have been straightforward. Yet the results were anything but. Some labs confidently flagged the right layers as enriched with microspherules, only for later analysis to show they had misidentified younger or older horizons. Others claimed to see no anomaly at all. For a scientific community that thrives on repeatable signals, this chaos raised troubling questions about observer bias, methodology, and even the definitions of what counted as an impact proxy. At the same time, questions of credibility began to swirl. Critics argued that if positive findings appeared only in a small circle of research groups, then confirmation bias might be at work. Supporters countered that outsiders were not using the specialized techniques required to detect fragile nanostructures. Both sides made valid points, but the tone of the conversation sometimes slipped into accusation. In the pages of journals and conference halls, one could sense the tension. Was this a genuine scientific puzzle, or a house of cards propped up by inconsistent data? It is worth remembering that scientific history is full of such controversies. Plate tectonics, for example, was once ridiculed until independent lines of evidence aligned. On the other hand, many once celebrated anomalies vanished after more rigorous testing. The Younger Dryas debate may one day fall into one of these categories. For now, the reproducibility problem remains central. Until multiple laboratories consistently detect the same proxies, dated with the same rigour, the extraordinary interpretation of a cosmic trigger will remain disputed. and perhaps this is a healthy state of affairs. Reproducibility wars are messy, but they force methods to improve, demand tighter standards, and discourage premature certainty. If the markers truly point to an impact, they will survive this gauntlet of scrutiny. If not, the scrutiny itself will have cleared the ground for better explanations. Either way, the dirt from 12,900 years ago still whispers stories. But for now, we are left arguing about whether those whispers are clear voices from the sky, or just the static of Earth's own restless processes. When the Younger Dryas is presented in popular accounts, it often comes across as a sudden, singular anomaly, an Ice Age twist that came out of nowhere. But when climate scientists line up the long ice core records from Greenland, a very different picture emerges. What seems like a once-in-history jolt actually resembles a repeating rhythm. These oscillations, first identified in the 1980s, are now known as Dansgaard-Oeschger events, or simply DO events. Over the last 80,000 years, the Greenland cores reveal more than 20 abrupt warmings followed by gradual coolings. Each of these events shares the same basic pattern, an astonishingly fast rise in temperature, sometimes 10 degrees Celsius in only a few decades, then a slow decline that ends in a cold plateau. The Younger Dryas fits this shape almost perfectly, except that it happened at the very end of the last glacial period. The fact that these cycles appear again and again tells us that the Earth's climate system has built-in modes of instability. Something in the interplay of ice sheets, oceans and atmosphere keeps producing the same rise and fall pattern, regardless of whether humans or mammoths happen to be watching. The challenge is that while we can see the pattern clearly in the ice, we still struggle to identify the precise switch that flips the system from warm to cold. Was it fresh water disrupting currents, shifts in wind belts, or oscillations in deep ocean circulation? Most likely it was some combination. What matters here is that the Younger Dryas does not stand alone. It belongs to a family of abrupt swings that punctuated the Ice Age like a drumbeat. This has important consequences for how we interpret the past. If you look only at the Younger Dryas in isolation, it is tempting to demand a dramatic trigger. If you place it alongside the earlier events, it becomes less of an outlier and more of an expected encore. For instance, around 37,000 years ago, another DO event shows nearly the same sequence. Rapid warming, long cooling, then a final plunge into cold that lasted centuries. Around 50,000 years ago, the same pattern appears again. These parallels make it difficult to insist that the Younger Dryas must have required something completely unique, like an extraterrestrial visitor. It might have been simply the last gasp of a repeating cycle that had already played out many times before. Still, even within this rhythm, the Younger Dryas holds its own fascination. It was the final cold snap before the Holocene, the one that immediately preceded the rise of agriculture and the growth of permanent villages. For the people living through it, it was not just another swing in the ice record, but a real environmental shift that demanded adaptation. This is the tension at the heart of the debate. From the perspective of climate science, the Younger Dryas may not be unique, but from the perspective of human history it mattered enormously. The haunting question, then, is whether we should treat the Younger Dryas as a special catastrophe, or as the predictable end of a cycle that was destined to fade anyway. If it is the latter, then the dramatic collapse into cold was not a freak accident, but part of the Earth's own breathing pattern. And if the Earth has breathed this way before, perhaps it will do so again, though next time under very different conditions, with billions of humans instead of scattered bands of hunter-gatherers. That possibility alone makes the lesson of these ancient cycles worth holding on to. If we step back even further, the idea that the Younger Dryas was simply one part of a recurring pattern becomes harder to dismiss. When researchers extend the Greenland ice core records back beyond 80,000 years, the picture that emerges is not one of stable, gentle climate shifts punctuated by a single oddity, but rather a world constantly jolted by quick swings. The longer we look, the clearer it becomes that abruptness is not an exception in Earth's climate system, it is a rule. Each Dansgaard-Oeschger event reveals itself as a set of fingerprints in the ice. Oxygen isotope ratios, dust levels, trapped gases. Together these layers show us that within the space of a human lifetime, the climate could swing from frigid to temperate and back again. To the hunters on the Mammoth steppe or the gatherers in the Levant, these changes would not have been visible on a graph. They would have appeared as the sudden return of winter where there should have been spring, the growth of glaciers on hillsides that had been bare, or the drying of rivers that communities had come to depend on. The reality is that the instability captured by the ice cores was lived instability. Some climatologists have pointed out that the Younger Dryas is not even the largest of these events in terms of the scale of cooling. Earlier cold phases during the glacial cycle lasted longer, or reached lower average temperatures. What makes the Younger Dryas distinctive is its timing. It came just when the planet seemed to be tipping decisively into a new interglacial. Imagine a symphony in which the final crescendo suddenly halts, replaced by a discordant pause before the music resumes. The abruptness is shocking not because such interruptions have never happened before, but because it came at the very moment an ending was expected. This is perhaps why the Younger Dryas has attracted so many alternative explanations and dramatic theories. Its position at the threshold of the Holocene gives it an outsized importance in human history. Agriculture arose not long after it ended, cities a little later. In retrospect, it feels almost like a curtain between worlds. But when you lay it alongside earlier Danskardurska events, it loses some of that aura of uniqueness. The curtain had been pulled many times before. It is simply that this was the last time it fell. And yet, even acknowledging this pattern does not explain the underlying mechanism. The great puzzle of DO events is that they repeat without being truly periodic. They are not like tides that can be predicted to the day. Instead, they arrive irregularly, with intervals ranging from 1,000 to several thousand years. Something in the Earth system is prone to tipping, but the timing depends on a tangled set of factors. That uncertainty leaves room for competing models, and it also explains why some scientists are reluctant to give up entirely on special triggers, like volcanic clusters or even impacts. If the system is unstable, perhaps outside nudges sometimes help push it over the edge. For me, the humbling part is this. Even after decades of drilling ice and running models, we cannot say with confidence why the Younger Dryas happened. We can only say that it fits into a broader story of climate chaos that has played out repeatedly during the Ice Age. The haunting thought is that if abrupt climate swings were part of the normal background then, they could also be part of our future. The Holocene has been unusually stable, but it would be naive to assume stability is permanent. If our ancestors could weather sudden plunges into cold, we should at least acknowledge that rapid shifts of another kind could confront us again, this time in a warming direction rather than a freezing one. Imagine waking one morning on the late Pleistocene landscape and finding that the horizon itself was on fire. The evidence tells us that around the onset of the Younger Dryas, something dramatic happened not just to glaciers and rainfall, but to the biosphere itself. Across cores of ice drilled from Greenland and Antarctica, across lakes that have preserved tens of thousands of years of pollen and ash, there is a signal of burning so large that some researchers have dared to estimate it may have consumed nearly a tenth of the Earth's vegetation. That number alone stops us in our tracks, because it suggests a planetary event, not a local disaster. But can we really imagine 9% of Earth's biomass vanishing in flames? And if so, what lit the match? The clearest markers of this inferno are the soot and ammonium peaks buried deep in the Greenland ice sheet. These substances are byproducts of intense combustion, whether of forests, grasslands, or even peat. Around 12,800 years ago, the levels of these compounds spike in a way that is difficult to reconcile with ordinary wildfires. Forest fires do happen, of course, and their signatures are found throughout ice core records. But the Younger Dryas onset stands out as sharper, taller, and more widespread. In fact, similar spikes are mirrored in ice drilled thousands of kilometers away in Antarctica and in cores taken from Russia. If this interpretation is right, then burning was not a regional accident but a synchronized global-scale event. Lake sediments tell a similar story. In North America, thin bands rich in charcoal suddenly appear, sometimes so dense that the sediments are almost black. In South America, there are traces of fires in peat bogs that had been stable for millennia. Across Europe and Asia, pollen assemblages shift in ways that suggest woodlands were thinned or cleared, consistent with massive burning. To the scientists piecing these strands together, the scale begins to look less like random coincidence and more like a single moment in Earth's environmental history. But here, the debate sharpens. Those who support the idea of a cosmic impact at the start of the Younger Dryas see these charcoal and soot spikes as exactly what would be expected if fragments of a comet or asteroid ignited the biosphere. An airburst over a continent, for example, could rain incandescent debris, scorching wide areas instantly. Even a strike into an ice sheet might throw enough hot ejecta into the atmosphere to light fires far afield. In this view, the fires are the smoking gun, literally, of an extraterrestrial trigger. Skeptics urge caution. Fire, they remind us, is a natural and ancient part of ecosystems. During the unstable climate swings of the late glacial, vegetation was stressed, fuels accumulated, and dry spells lengthened. In such conditions, lightning alone could have sparked more frequent and larger fires. A warmer interlude before the Younger Dryas may have built up forests, which then became tinder when conditions suddenly turned drier and colder. This line of reasoning suggests that Earth itself had prepared its own pyre, and it needed no cosmic match to light it. There is also the question of scale. Is 9% of global biomass realistic? Or is it an overinterpretation of chemical spikes? Models of atmospheric transport remind us that soot and ammonium from burning in one region can circle the globe, settling into distant ice sheets. A superfire in North America, for example, could conceivably leave its fingerprints in Greenland and Antarctica. That possibility would reduce the estimate of global biomass burned, while still leaving a picture of extraordinary devastation in one hemisphere. What is undeniable is that for plants, animals, and humans alive at that moment, landscapes were altered in the span of a generation. Imagine valleys filled with charred trees, herds forced to migrate across scorched plains, smoke dimming the skies. Such events would have added chaos to already fragile ecologies and may have compounded the stresses of abrupt cooling. As scientists, we are left with a haunting question. Were these global fires the signature of a cosmic visitor, a fragmenting comet that changed the course of the Earth's history? Or were they simply the Earth's own ecological tinderbox catching fire during a time of extraordinary instability? The ice cores will keep their counsel, the charcoal bands will remain silent. For now, we have to live with both possibilities, humbly aware that in science, as in life, absence of certainty is the rule, not the exception. The evidence for fire during this interval is not confined to the microscopic traces buried in ice or sediment. It is also written into the shifting patterns of vegetation. Fossil pollen assemblages, carefully counted grain by grain, reveal sudden declines in tree species that had been expanding after the last glacial maximum. In parts of Europe, birch and pine show abrupt contractions, while grasses and herbaceous plants surge in their place. In North America, oak and spruce records are punctuated by gaps where forest cover thinned dramatically. Such transitions are consistent with ecosystems recovering after fire, when opportunistic species colonize the open ground left behind. These ecological scars are not easily dismissed as ordinary variability. Forests take centuries to regrow after widespread burning, and the recovery curves preserved in pollen data stretch long into the Younger Dryas. What this suggests is that the event was not just a cluster of local fires that left their mark for a season or two. Instead, it was a profound ecological reset in many regions, one that required entire generations of plant and animal communities to rebuild themselves. The consequences would have been felt by every organism tied to those ecosystems. Herbivores depending on forest browse would have been forced into marginal habitats. Carnivores would have followed, their ranges squeezed. For humans, who at that time relied heavily on hunting and gathering, the fires must have been both a disaster and an opportunity. Burnt landscapes attract grazing animals, and freshly opened plains can support different food webs. But the dislocation also meant scarcity, unpredictability, and competition. Survival in such times required flexibility, something our species seems to have had in abundance. One of the most debated aspects of this fire evidence is the synchronicity across continents. If we were to see charcoal peaks in one region alone, the explanation could rest comfortably on local droughts or storms. But when multiple regions, thousands of kilometers apart, record elevated burning at roughly the same moment, the search for a unifying trigger intensifies. Was the climate itself globally shifting in a way that favoured fire everywhere? Or do these convergences point to a singular dramatic ignition source? This is the crux of the argument between natural cycle advocates and proponents of the impact hypothesis. Adding to the complexity, the chemical fingerprints of the combustion are not all identical. In some cores, the ratio of soot to ammonium suggests fast, hot burns of woody fuel. In others, the signals look more like smouldering peat or grassland fires. This diversity may indicate that the trigger, whatever it was, did not cause uniform burning, but instead unleashed many different fire regimes depending on what vegetation was available. That patchwork outcome complicates the narrative, but also makes it more plausible. Earth was not a uniform tinderbox, but a patchy mosaic of landscapes, each responding to stress in its own way. Another dimension to consider is the atmospheric impact. Models suggest that burning on the proposed scale could have released immense amounts of carbon dioxide and particulates into the sky. Short term, the soot could have darkened skies, cooling the surface by blocking sunlight. Longer term, greenhouse gases from combustion might have countered that effect, adding heat back into the system. This duality, cooling haze followed by gradual warming, mirrors the kind of climate whiplash we see in the records. Yet teasing apart which was cause and which was effect remains difficult. Did cooling conditions foster more fire, or did fire itself reinforce cooling? The feedbacks run in both directions. The haunting question remains: can we ever pin down whether these immense fires were an inevitable byproduct of climate chaos or the fallout of a celestial accident? As of now, both paths remain open, and each adds a layer of awe to our understanding. If Earth lit its own fires, it shows how precarious life can be under shifting climate. If a comet lit them, it shows how vulnerable our world is to cosmic chance. Either way, the story is the same. At the dawn of the Younger Dryas, the planet burned, and every creature living then carried the scars of smoke and ash into their future. Across the continents, as the Younger Dryas unfolded, some of the most iconic animals that had shared the Ice Age world with us began to vanish. Mammoths, mastodons, giant sloths, saber-toothed cats, and the great Irish elk had survived for millennia through glacial advances and retreats. They had weathered colder periods, adapted to fluctuating landscapes, and coexisted with multiple human species. Yet in the span of a few thousand years at the very end of the Pleistocene, their numbers dwindled and their shadows disappeared from the plains. What changed? Was it the Younger Dryas chill itself, tightening ecosystems until they could no longer support giants? Or was it the arrival and ingenuity of humans, wielding tools, fire, and cooperation in ways that animals had never before encountered? The archaeological record gives us vivid clues that human hunting played a role. In central Mexico, researchers uncovered pits measuring more than 20 meters across and nearly 2 meters deep, dug deliberately into the landscape. Within these traps lay the remains of at least 14 mammoths, their bones showing cut marks and deliberate butchering. All of them shared a peculiar detail. The left shoulder blade was missing, suggesting either ritual removal or a repeated butchery practice. For hunters who had just crossed into new territories, digging such enormous pits was no small feat. It tells us that groups coordinated labour, anticipated herd movements, and constructed elaborate traps to funnel these animals to their deaths. It is hard to argue that megafauna were simply dying off on their own when such direct evidence of human predation exists. Elsewhere across North America, mammoth kill sites punctuate the record. Tools embedded in rib bones, cut marks etched into pelvises, and bones cracked for marrow extraction all attest that mammoths were not just occasional prey, but part of the human menu. In Europe and Siberia, the story repeats. Mammoth bones were carved into huts, tusks shaped into spears, hides used for clothing and shelter. These were not rare encounters. Humans and megafauna were entangled in ways that left deep marks on both sides. Yet climate cannot be ruled out. Genetic studies and fossil distribution maps suggest that mammoth populations were already fragmenting into smaller refugia even before the Younger Dryas. As warming and cooling oscillated, the grasslands they depended on shrank, replaced by forests in some regions and deserts in others. Their ranges contracted, leaving isolated populations vulnerable to disease, inbreeding, and the chance strikes of hunters. The Younger Dryas may have accelerated this process by shortening growing seasons and drying landscapes, tipping the balance for species already stressed. Perhaps the most poignant evidence against climate alone as the sole culprit comes from the outliers. On Wrangel Island in the Siberian Arctic, mammoths survived until roughly 4,000 years ago, long after pyramids were already rising along the Nile. These last survivors lived in a constrained ecosystem, cut off from continental predators, but also shielded from the worst swings of climate. Their persistence shows that mammoths could endure even in reduced numbers if circumstances allowed. What ultimately doomed them was not the cold or heat in itself, but the shrinking of safe havens where they could escape both environmental change and human pursuit. This dual lens, climate-squeezing habitats and humans exploiting the survivors, may be the most balanced explanation for the extinctions. Where refugia persisted, animals could hold on until the human footprint reached them. Where climate change struck hardest, herds dwindled and became easy targets for hunters. Neither force alone is sufficient to explain the staggered species-by-species timing of extinctions across the globe. Together, however, they paint a picture of vulnerability meeting opportunity. And so the haunting question lingers. Were the mammoths and their Ice Age kin fated to disappear no matter what? Or did our arrival at the cusp of the Younger Dryas deliver the final push? We cannot rewind the Pleistocene to run the experiment twice. All we can do is weigh the bones, read the sediments, and reflect on the paradox that humanity's rise coincided so precisely with the fading of Earth's giants. Another layer of this story lies in the uneven timing of extinctions. If climate alone were responsible, one might expect a more synchronized pattern across continents, with species collapsing simultaneously as the Younger Dryas reshaped environments. But the fossil record tells a more complicated tale. In South America, giant ground sloths lingered until roughly 10,000 years ago, long after mammoths in many parts of North America had vanished. In Europe, the Irish elk fell at different times depending on region, some herds surviving longer in refuges than others. In North America, mastodons disappeared earlier in certain areas than mammoths, despite overlapping ranges. This patchwork chronology undermines the idea of a single sweeping catastrophe. Instead, it suggests a mosaic of local pressures, climate squeezing here, hunting intensifying there, gradually eroding the megafaunal world. Archaeological discoveries add further nuance. At some kill sites, bones show clear butchery marks and tool associations, leaving little doubt of human involvement. Yet at others, skeletons lie scattered without signs of human interference, hinting that disease, starvation, or environmental stress also played a role. The challenge for scientists is disentangling these overlapping signals. Did hunters deliver the coup de grace to herds already collapsing from lack of forage? Or did climatic downturns thin populations to the point where hunting pressure suddenly became unsustainable? The truth may lie in the interplay, a perfect storm of ecological stress and human exploitation. Modern genetic research has sharpened this picture. By sequencing ancient DNA from preserved bones and tusks, scientists have tracked changes in effective population size over time. Many species, including mammoths, show sharp declines before their final disappearance, consistent with small, isolated groups struggling to maintain diversity. These genetic bottlenecks made populations fragile, less able to adapt to sudden shocks such as rapid climate swings or increased hunting pressure. In essence, extinction was not a single blow, but a cumulative process, with vulnerabilities building until survival became untenable. The persistence of mammoths on Wrangel Island adds a poignant epilogue. Their isolation preserved them from the hunters and habitat changes that swept continental populations away, but their genetic diversity dwindled to critically low levels. Studies of their genomes show signs of accumulating mutations, degraded fertility, and weakened resilience. By the time they finally died out around 2000 BCE, they were shadows of their former selves. Their story underscores how survival in refugia could delay, but not ultimately prevent extinction, once species had crossed a certain threshold of vulnerability. This broader lens also reminds us that humans were not passive observers of these declines. By this point in history, our species had expanded across nearly every continent, adapting to deserts, forests, tundras, and coasts. Wherever we arrived, ecosystems shifted. Fire was used to shape landscapes, hunting strategies grew more sophisticated, and prey animals found themselves facing not only natural predators, but a species uniquely capable of planning, coordinating, and persisting. The very traits that made Homo sapiens successful, adaptability, cooperation, ingenuity, were the same traits that spelled trouble for the giants of the Ice Age. And yet, to imagine humans as sole executioners oversimplifies the story. The climatic background of the Younger Dryas cannot be erased from the record. Shorter growing seasons, advancing glaciers, and shifting vegetation patterns all constrained the resources on which large animals depended. Even without human hunting, many populations might have collapsed. What our presence did was amplify those pressures, hastening a process already underway. When we step back from the bones, the pits, and the pollen, what remains is a sobering reflection. The megafaunal extinctions of the late Pleistocene were not a single event with a single cause. They were the outcome of converging forces, environmental instability and human expansion, that together reshaped the planet. The haunting question is not just why mammoths and mastodons vanished, but what their disappearance says about the fragility of a large species in the face of rapid change. If giants could fall then, under the twin pressures of climate and humanity, what does that suggest for the megafauna that remain today? Another layer of this story lies in the uneven timing of extinctions. If climate alone were responsible, one might expect a more synchronized pattern across continents, with species collapsing simultaneously as the Younger Dryas reshaped environments. But the fossil record tells a more complicated tale. In South America, giant ground sloths lingered until roughly 10,000 years ago, long after mammoths in many parts of North America had vanished. In Europe, the Irish elk fell at different times depending on region, some herds surviving longer in refuges than others. In North America, mastodons disappeared earlier in certain areas than mammoths, despite overlapping ranges. This patchwork chronology undermines the idea of a single sweeping catastrophe. Instead, it suggests a mosaic of local pressures, climate squeezing here, hunting intensifying there, gradually eroding the megafaunal world. Archaeological discoveries add further nuance. At some kill sites, bones show clear butchery marks and tool associations, leaving little doubt of human involvement. Yet at others, skeletons lie scattered without signs of human interference, hinting that disease, starvation, or environmental stress also played a role. The challenge for scientists is disentangling these overlapping signals. Did hunters deliver the coup de grace to herds already collapsing from lack of forage? Or did climatic downturns thin populations to the point where hunting pressure suddenly became unsustainable? The truth may lie in the interplay, a perfect storm of ecological stress and human exploitation. Modern genetic research has sharpened this picture. By sequencing ancient DNA from preserved bones and tusks, scientists have tracked changes in effective population size over time. Many species, including mammoths, show sharp declines before their final disappearance, consistent with small, isolated groups struggling to maintain diversity. These genetic bottlenecks made populations fragile, less able to adapt to sudden shocks such as rapid climate swings or increased hunting pressure. In essence, extinction was not a single blow, but a cumulative process, with vulnerabilities building until survival became untenable. The persistence of mammoths on Wrangel Island adds a poignant epilogue. Their isolation preserved them from the hunters and habitat changes that swept continental populations away, but their genetic diversity dwindled to critically low levels. Studies of their genomes show signs of accumulating mutations, degraded fertility, and weakened resilience. By the time they finally died out around 2000 BCE, they were shadows of their former selves. Their story underscores how survival in refugia could delay, but not ultimately prevent extinction, once species had crossed a certain threshold of vulnerability. This broader lens also reminds us that humans were not passive observers of these declines. By this point in history, our species had expanded across nearly every continent, adapting to deserts, forests, tundras, and coasts. Wherever we arrived, ecosystems shifted. Fire was used to shape landscapes, hunting strategies grew more sophisticated, and prey animals found themselves facing not only natural predators, but a species uniquely capable of planning, coordinating, and persisting. The very traits that made Homo sapiens successful, adaptability, cooperation, ingenuity, were the same traits that spelled trouble for the giants of the Ice Age. And yet, to imagine humans as sole executioners oversimplifies the story. The climatic background of the Younger Dryas cannot be erased from the record. Shorter growing seasons, advancing glaciers, and shifting vegetation patterns all constrained the resources on which large animals depended. Even without human hunting, many populations might have collapsed. What our presence did was amplify those pressures, hastening a process already underway. When we step back from the bones, the pits, and the pollen, what remains is a sobering reflection. The megafaunal extinctions of the late Pleistocene were not a single event with a single cause. They were the outcome of converging forces, environmental instability and human expansion, that together reshaped the planet. The haunting question is not just why mammoths and mastodons vanished, but what their disappearance says about the fragility of a large species in the face of rapid change. If giants could fall then, under the twin pressures of climate and humanity, what does that suggest for the megafauna that remain today? When the Younger Dryas is invoked in popular writing, it is often paired with another apparent mystery, the supposed disappearance of the Clovis culture of North America. The narrative is simple and dramatic. Around 13,000 years ago, so the story goes, a comet struck, the climate lurched, the mammoths fell, and the Clovis people vanished. But as with so many ideas in archaeology, the reality is far more complicated, less cinematic, and arguably more interesting. Instead of a sudden vanishing, what we see in the record looks more like transformation, a pattern of regional adjustments to new circumstances rather than a single dramatic collapse. Clovis sites are best known for their iconic fluted projectile points, long slender blades with a channel carved from base to tip. These artifacts appear across much of North America, between roughly 13,300 and 12,800 years ago. The spread is astonishing, from the Great Plains to the American Southeast, and even into parts of Mexico. For much of the 20th century, Clovis was imagined as the first great migration pulse of humans into the continent, a big game-hunting culture sweeping across the land. But even before the Younger Dryas entered the conversation, evidence was already complicating that tidy picture. Clovis was never monolithic. Its distribution was patchy, its toolkit varied by region, and many groups clearly used resources beyond big game. So what happened as the Younger Dryas began? The archaeological record does not show Clovis settlements abruptly ceasing, nor does it show human absence. Instead, it shows regional continuity and transition. In the western Great Plains and the Rocky Mountains, distinctive fulsome points begin to appear soon after 12,800 years ago. These points are smaller, thinner, and crafted with extraordinary precision, often used in communal bison hunts. Yet when archaeologists look closely, they find overlap. At some sites, Clovis and fulsome artifacts appear together, suggesting not replacement but adaptation. Clovis technology evolving into new forms as herds and landscapes shifted. Elsewhere, in the American Southeast, different traditions emerged altogether. In places like the Carolinas, Swanee and Simpson points appear, distinct in form but clearly part of the same continuum of technological innovation. In the Southwest, other local styles proliferated. The picture that emerges is not a cultural vacuum, but a mosaic of regional adaptations to changing prey, shifting climate and altered landscapes. The so-called disappearance of Clovis may therefore be better understood as diversification, a branching into multiple traditions rather than a sudden extinction. Mobility was a key factor. Clovis groups, like their successors, were highly mobile foragers, following herds and seasonal resources. Their archaeological signature is thin, scattered across thousands of kilometres, leaving behind mostly stone tools rather than permanent dwellings. This mobility means their presence is harder to track than settled farming societies of later times. A gap in artefacts does not necessarily mean absence. It may mean groups moved on, changed their toolkits, or left behind traces that have yet to be discovered. The idea that Clovis was wiped out in a single cataclysm also neglects the resilience of human societies. These were populations adapted to extremes, capable of surviving both glacial and interglacial climates. Their toolkits were flexible, their social networks wide-ranging. There is little reason to believe they could not adapt to new challenges. Indeed, the very fact that human populations thrived across the Americas, throughout the Younger Dryas and beyond, is evidence that whatever happened to Clovis, it was not annihilation. This is not to say that life was easy. Climatic instability, shrinking ranges of prey animals and unfamiliar conditions would all have challenged these groups. The Younger Dryas may have accelerated the pace of cultural change, forcing technological innovations and adjustments in subsistence strategies. But the notion of a neat before and after dividing line, with Clovis on one side and emptiness on the other, is not supported by the evidence. Instead, the archaeological record tells a story of continuity through change, of societies reshaping themselves in response to a new world. In the end, the haunting question is not why Clovis disappeared, but why we ever thought it had. Perhaps the appeal lay in its neatness, the allure of a mystery solved by a single dramatic event. Yet archaeology, like climate science, resists such simplicity. What we find in the ground is messier, layered, ambiguous, and human. Cultures shift, adapt, branch, and merge. Clovis was no different. Its legacy lived on, not in vanishing, but in transformation. If the Younger Dryas was truly a global catastrophe, then the expectation is simple. Every corner of the Earth should show its mark. Yet when researchers turned their eyes south of the equator, the story became muddier, more regional, and sometimes outright contradictory. Some places seem to echo the northern chill, while others appear to have marched to their own rhythm, either staying stable or even getting wetter and more productive. This geographic patchwork challenges the very notion of a single global event, raising questions not only about what caused the Younger Dryas, but about how climate itself can fracture into very different experiences depending on latitude and geography. In northern South America, sediment cores from Lake Valencia in Venezuela tell a clear story of cooling and drying at the onset of the Younger Dryas. Vegetation records suggest a decline in tropical forests, replaced by more open, arid landscapes. Pollen trapped in the lake mud shows less diversity and hints at ecological stress. To a population of foraging peoples depending on the bounty of fruits, nuts, and river resources, this would not have gone unnoticed. The tropical belt, often imagined as immune to ice age swings, was in fact sensitive to atmospheric changes rippling through global systems. Yet even here, the signal was not identical to the frozen north. Cooling was real, but its expression was muted, stretched over centuries rather than abrupt decades, more a steady dimming of the tropical greenhouse than a sudden plunge into cold. Travel eastward and southward, however, the evidence shifts again. In parts of the South Pacific, proxies tell of wetter conditions, not drier ones. In Australia, lake levels at sites such as Lake Eyre suggest that during the Younger Dryas interval, the interior may have experienced increased rainfall. Instead of drought, some regions received replenishment, and river systems swelled. For the Aboriginal peoples who had already lived on this continent for tens of thousands of years, this may have meant new opportunities to hunt and gather, rather than sudden collapse. The stark contrast with Venezuela underlines an essential truth of paleoclimate. What feels like catastrophe in one region may be boon in another. Antarctica, always the elephant in the paleoclimatic room, complicates matters further. Ice cores from the southern continent show signals that do not align neatly with Greenland's. Where Greenland records a sharp cooling at the Younger Dryas onset, Antarctic cores sometimes show modest warming or complex variability. This pattern has been described as a bipolar seesaw, where heat storage and release between hemispheres seem to oscillate. When the north plunges into chill, the south can warm slightly and vice versa. The underlying mechanisms may involve ocean circulation and the way heat is transferred across basins. But whatever the cause, the result is that Antarctica does not mirror Greenland. Instead, it plays a complementary note in a global symphony of climate change. South America beyond Venezuela adds yet another wrinkle. In Patagonia, glaciers advance during the Younger Dryas interval, a clear signal of local cooling. But in the Amazon basin, evidence is far patchier, with some cores showing little change and others suggesting modest shifts in rainfall. Even within a single continent, the experience of the Younger Dryas depended heavily on geography, altitude, and proximity to oceans. All of this raises a haunting question. If the Younger Dryas was driven by a single catastrophic cause, why do we see such uneven fingerprints across the planet? If a comet truly struck, or if massive floods disrupted global systems, should the world not have reacted in a more uniform fashion? Yet if the event was simply one of many oscillations in Earth's climate machinery, then the patchwork makes more sense. Climate is not a single switch, but a web of interconnected systems. The seesaw between hemispheres, the contrast between tropics and temperate zones, the divergence of rainfall patterns, all of these remind us that even when Earth changes suddenly, it does not change in the same way everywhere. The puzzle of the Southern Hemisphere forces humility into the debate. It warns us against assuming that the spectacular records of Greenland automatically speak for the whole world. They may instead speak for a hemisphere caught in its own feedback loops. Meanwhile, the peoples of South America, Africa and Australia were living through their own versions of this shift. Versions that may have felt less apocalyptic but no less real. The Younger Dryas, in this sense, was both global and local, a worldwide climate event expressed through 1,000 regional stories. One important angle often overlooked in the Southern Hemisphere is how ecosystems themselves bore witness to the shifts. In New Zealand, pollen records reveal transitions in plant communities that hint at temperature fluctuations around the Younger Dryas interval. Alpine herbs expanded while forests temporarily contracted, suggesting that even regions far removed from the North Atlantic were not immune to subtle ripples in the climate system. Yet these shifts were not catastrophic collapses. Forests returned, biodiversity endured, and people adapted. It was change, yes, but not devastation. This subtlety adds weight to the argument that the Younger Dryas was not a monolithic ice grip over the globe, but rather a set of uneven disturbances, locally amplified or muted depending on latitude and geography. Africa adds another critical piece to the puzzle. Sediment cores from East African lakes like Lake Victoria and Lake Tanganyika tell of shifting rainfall patterns during this period. Some cores suggest heightened aridity, which would have tested the resilience of human groups who already relied on fragile ecosystems at the edge of the savanna. Others point to relative stability, implying that the climate system here operated under a slightly different rhythm than the North Atlantic. These contrasting stories remind us that global events in climate history often look more like mosaics than single brushstrokes. Marine records from the Indian Ocean complicate things further still. Temperature reconstructions show modest cooling that overlaps with the Younger Dryas, but the signal is not sharp or sudden. Instead of the dramatic plunge seen in Greenland, the Indian Ocean's record appears buffered, as though the Great Basin absorbed some of the instability and smoothed it out. For communities along its coasts, the difference between buffered and abrupt might have meant the difference between steady adaptation and sudden disruption. The larger lesson from these southern and tropical records is that Earth's climate engine has never been a simple global thermostat. It is more like a series of interlinked gears. When one gear jerks, such as the North Atlantic circulation, others respond in complex ways, some speeding up, others slowing down, and some barely moving at all. The Younger Dryas, when seen from south of the equator, forces us to confront this complexity. What feels like a crisis in one hemisphere might manifest as resilience, opportunity, or even improvement in another. The haunting question that lingers is whether we overemphasize the catastrophic when the evidence is uneven. If Australia grew wetter, if parts of Africa muddled through, and if Antarctica played its own counterpoint, can we really say the whole world was plunged into crisis? Or should we instead recognize the Younger Dryas as a reminder that Earth's climate system resists easy labels, expressing its turmoil differently across the globe? One important angle often overlooked in the Southern Hemisphere is how ecosystems themselves bore witness to the shifts. In New Zealand, pollen records reveal transitions in plant communities that hint at temperature fluctuations around the Younger Dryas interval. Alpine herbs expanded while forests temporarily contracted, suggesting that even regions far removed from the North Atlantic were not immune to subtle ripples in the climate system. Yet these shifts were not catastrophic collapses. Forests returned, biodiversity endured, and people adapted. It was change, yes, but not devastation. This subtlety adds weight to the argument that the Younger Dryas was not a monolithic ice grip over the globe, but rather a set of uneven disturbances, locally amplified or muted depending on latitude and geography. Africa adds another critical piece to the puzzle. Sediment cores from East African lakes like Lake Victoria and Lake Tanganyika tell of shifting rainfall patterns during this period. Some cores suggest heightened aridity, which would have tested the resilience of human groups who already relied on fragile ecosystems at the edge of the savanna. Others point to relative stability, implying that the climate system here operated under a slightly different rhythm than the North Atlantic. These contrasting stories remind us that global events in climate history often look more like mosaics than single brushstrokes. Marine records from the Indian Ocean complicate things further still. Temperature reconstructions show modest cooling that overlaps with the Younger Dryas, but the signal is not sharp or sudden. Instead of the dramatic plunge seen in Greenland, the Indian Ocean's record appears buffered, as though the Great Basin absorbed some of the instability and smoothed it out. For communities along its coasts, the difference between buffered and abrupt might have meant the difference between steady adaptation and sudden disruption. The larger lesson from these southern and tropical records is that Earth's climate engine has never been a simple global thermostat. It is more like a series of interlinked gears. When one gear jerks, such as the North Atlantic circulation, others respond in complex ways, some speeding up, others slowing down, and some barely moving at all. The Younger Dryas, when seen from south of the equator, forces us to confront this complexity. What feels like a crisis in one hemisphere might manifest as resilience, opportunity, or even improvement in another. The haunting question that lingers is whether we overemphasize the catastrophic when the evidence is uneven. If Australia grew wetter, if parts of Africa muddled through, and if Antarctica played its own counterpoint, can we really say the whole world was plunged into crisis? Or should we instead recognise the Younger Dryas as a reminder that Earth's climate system resists easy labels, expressing its turmoil differently across the globe? One of the strongest arguments for a layered explanation is the timing. Each factor alone could be debated endlessly, but together they overlap in ways that are difficult to dismiss. The ice sheets were already weakened by centuries of warming, storing enormous volumes of meltwater in unstable lakes. Volcanic eruptions clustered in the centuries just before and during the Younger Dryas, injecting sulfate and ash into the atmosphere. Charcoal and soot evidence point to widespread burning that could have been sparked either by lightning in tinder-dry landscapes or by something more dramatic from above. Humans, equipped with increasingly sophisticated tools, were pressing harder on the very species that were simultaneously losing their habitats. When these elements align, they do not simply add, they multiply. Each stress feeds into the others, raising the chance of irreversible tipping points. This perspective reframes the debate. Rather than asking which theory wins, perhaps the more productive question is how these forces interacted. A volcanic eruption during a stable climate might not lead to long-term cooling, but paired with a weakened ocean conveyor, it could tip the balance. An extraterrestrial airburst on its own might ignite regional fires, but set against a background of drought and ecosystem stress, those fires could escalate into continent-spanning events. Human hunting in lush environments may not doom megafauna, but in landscapes already fragmented by cold, aridity, and fire, the pressure could prove fatal. Each explanation, once pitted against the others, begins to look more plausible when seen as part of a chain reaction. There is also a philosophical lesson here. The desire for a single neat cause reflects how our minds like to simplify history. We want one dramatic culprit to explain upheaval. Yet Earth's story rarely grants us that simplicity. The Younger Dryas reminds us that the past unfolded through webs of interactions, where natural forces and human decisions were entangled. The all-of-the-above model might not be as cinematic as a lone comet streaking through the sky, but it carries a sobering power of its own. It shows that collapse can emerge not from one overwhelming blow, but from many smaller ones converging at once. This layered view leaves us with a haunting question. Are we still tempted to search for singular explanations in our own time, when crises are more often the result of many stresses colliding? If the Younger Dryas was indeed the product of ice, fire, air, and human hands all working together, then it is not just a mystery of the past. It is also a warning about the present, when once again Earth's systems strain under multiple pressures that do not wait politely to take their turns. At the close of the Younger Dryas, around 11,700 years before the present, the curtain rose on a new chapter in the story of our species. The sudden chill, whether sparked by ice, ocean, fire, or sky, gave way to warmth again, and this time the warmth stayed. The Holocene began, the epoch in which every recorded human story has been told. Yet when we look back at that boundary moment, we are left not with certainty but with ambiguity. The great questions of what ended the Ice Age and why the last mammoths dwindled into obscurity do not yield simple answers, only interwoven possibilities. And it is within that uncertainty that the haunting power of the Younger Dryas resides. For the people alive then, the return of warmth was not a chapter break in a textbook. It was the difference between starvation and abundance, between icy winds scouring plains and meadows greening with edible plants. In the Levant, the Natufian people had been experimenting with wild cereals for centuries, building more permanent settlements along fertile valleys. The abrupt cold forced them to scatter again, to lean once more on mobility and resilience. When the warmth returned, so too did their villages, but this time with deeper commitment to cultivation. Out of a period of collapse and reorganisation came the first hesitant steps toward agriculture. It is striking to think that farming, which reshaped the destiny of humanity, may have been quickened not by a steady climate, but by one of its most violent oscillations. Elsewhere, echoes of the old Ice Age lingered. In isolated refuges like Wrangel Island in the Arctic Ocean, mammoths survived thousands of years longer than on the mainland. They carried on until around 2,000 years before the Common Era, living ghosts of an Ice Age world. Their persistence is a reminder that extinctions are rarely absolute events marked by a single date. They are long tails, uneven declines, where species fade from continent to continent, leaving pockets of survival that gradually wink out. When we tell the story of the Younger Dryas as the end of mammoths, we oversimplify. The truth is subtler and sadder, a story of dwindling possibilities stretched over millennia. What makes this period so haunting is that it straddles myth and science, memory and data. The Holocene that followed is the world we know, the one in which every culture, city and invention arose. Yet it was born out of mystery. Was there a comet streaking across the skies of our ancestors, or was the real culprit the deep ocean reorganising its currents far beneath their feet? Was the black smoke they may have seen the mark of burning forests lit by falling fire, or the slower but equally devastating work of drought? The evidence is there in ice, in soil, in bones, but it resists unambiguous interpretation. And so the birth of our world, the threshold moment between Ice Age and civilization, is marked not by clarity but by questions. Perhaps that is fitting. Humanity did not emerge into a stable Eden, but into a climate system full of jolts and surprises. The Natufians learned that permanence is fragile, mammoths learned that size is no shield, and even the mightiest ice sheets learned that they could vanish in a geological instant. Out of that instability came resilience, adaptation, and eventually the capacity to shape environments ourselves. Whether or not the Younger Dryas was triggered by a cosmic visitor, it left behind the conditions in which our story could unfold. And so, we are left with a choice. We can tell the tale as a cosmic catastrophe that nearly ended us, or as a natural cycle in which we were simply one more actor, adjusting to forces beyond our control. Both stories have merit, and perhaps both are true in different ways. What matters is that out of ambiguity came the familiar world, our present comforts, our civilizations, even our debates over what truly happened, all rest on that unstable foundation. If there is a lesson in this haunting transition, it is not to expect simple answers from deep time. Earth is a tangled system, and our place in it is precarious. The Younger Dryas lingers as a reminder that our beginnings were shadowed by uncertainty, and that sometimes it is the questions themselves, not the answers, that define us. Did a comet shape the birth of our world, or are we chasing shadows in ice and soil? That question will likely follow us for as long as we keep asking. Thank you, fellow sapiens, for wandering this timeline with me, for drifting into deep time, for slowing down and remembering. If this helped you fall asleep, helped you study, or simply helped you step out of the noise for a while, thank you for being here. If you think more people should know this story, you know what to do. Like, subscribe, share it with the sapiens in your life, and tell me, are you listening before bed, while working, or somewhere in the world I can only imagine? And as always, stay curious, stay calm. I'll see you in the next story.